Right now, you're holding a pocket-sized supercomputer that can answer any question, connect you to anyone, even predict the weather. But what if I told you that 2,000 years ago, ancient engineers were building devices just as sophisticated, machines that tracked the stars with pinpoint accuracy, generated electricity centuries before batteries were invented, and even predicted earthquakes better than modern sensors? These weren't primitive tools, they were technological masterpieces lost to time. Over the next few minutes, we'll uncover 50 of history's most mind-blowing inventions that could rival what's in your home today. From steam-powered robots in Alexandria to earthquake detectors in ancient China, these forgotten marvels will make you question everything you thought you knew about the past. Stick around, because by the end of this journey, you'll never look at history the same way again. Now, let's turn our attention to the first marvel on our list, a device so advanced it shattered our understanding of ancient technology, the Antikythera Mechanism. Discovered in a shipwreck off the coast of Greece in 1901, this bronze and clockwork artifact wasn't fully understood until decades later, when modern imaging revealed its true complexity. What at first appeared to be a corroded lump of metal turned out to be the world's first known analog computer, a masterpiece of engineering that tracked celestial movements with astonishing precision. Imagine a handheld device roughly the size of a shoebox, filled with more than 30 interlocking bronze gears. Each gear was meticulously calibrated to mimic the motion of the sun, moon, and planets. The mechanism didn't just display the time or date. It predicted solar eclipses years in advance, charted the phases of the moon, and even accounted for the irregular orbit of Mercury. To put it simply, this was an ancient Greek astronomer's ultimate tool, a pocket-sized planetarium that could calculate celestial events with an accuracy that wouldn't be matched for over 1,000 years. But here's where it gets even more fascinating. The Antikythera Mechanism didn't just track the sky, it encoded the astronomical knowledge of its time. Scholars believe it may have been used to schedule religious festivals, agricultural cycles, and even the Olympic Games. Some of its gears were dedicated to the Saros cycle, a repeating pattern of eclipses that ancient Greeks used to predict when the moon would blot out the sun. And unlike modern computers that rely on electricity, this device was entirely mechanical, powered by a simple hand crank. What truly sets the Antikythera Mechanism apart is how it challenges our assumptions about ancient technology. For centuries, historians believed that complex geared devices like this didn't emerge until the Middle Ages with the invention of mechanical clocks. Yet here was proof that the ancient Greeks had not only conceived of such technology but perfected it. Even today, researchers are still uncovering its secrets. High-resolution scans have revealed hidden inscriptions, a user manual of sorts, that explain how to operate its dials and interpret its predictions. So why does this matter? Because the Antikythera Mechanism forces us to rethink what ancient civilizations were capable of. It wasn't just a lucky discovery, it was a glimpse into a world where engineering and astronomy intersected in ways we're only beginning to comprehend. And as we move forward in our journey through history's lost inventions, keep this in mind. If the Greeks could build a computer 2,000 years ago, what other groundbreaking devices are still waiting to be uncovered? Now let's delve into the lasting impact of the Antikythera Mechanism and how its discovery continues to spark debates and inspire modern innovations. The mystery of this ancient device has captivated scientists and historians for over a century, leading to numerous attempts to recreate its intricate design. In 2006, a team of researchers used advanced X-ray tomography to peer inside the corroded fragments, revealing hidden gears and inscriptions. Armed with this data, experts like Michael Wright, a former curator at London's Science Museum, painstakingly built functional replicas. These reconstructions confirmed that the mechanism wasn't just a theoretical marvel, it worked with startling precision. One model even accurately predicted the solar eclipse of 2008, proving the Greeks had mastered celestial mechanics long before the telescope was invented. But the Antikythera Mechanism's origins remain shrouded in controversy. While most agree it was likely built around 80 to 60 BC, no one knows for certain who designed it. Some scholars point to the island of Rhodes, home to famed astronomers like Hipparchus, whose theories on lunar motion align with the device's calculations. Others suggest it may have been crafted in Syracuse, where Archimedes reportedly created a similar celestial globe. The absence of any other surviving examples raises a haunting question. Was this mechanism a one-of-a-kind masterpiece, or were there others lost to time? What makes this artifact so revolutionary is how it upends our view of ancient technological progress. For decades, historians assumed complex gear systems didn't appear until medieval clock towers. Yet the Antikythera Mechanism's existence suggests the Greeks, or perhaps even earlier civilizations, had engineering knowledge far beyond what we've credited them for. Its gears employ a sophisticated differential mechanism, a technology later reinvented in the 19th century for modern automobiles. This wasn't just luck. It was the product of deliberate, advanced mathematical and mechanical understanding. The device's legacy extends beyond academia. Engineers today study its design for insights into compact, efficient machinery. Its ability to model irregular celestial orbits without digital components has inspired analog computing projects, proving that sometimes the old ways still hold untapped potential. Meanwhile, historians are left wondering, if a device this advanced existed 2,000 years ago, what other inventions might have been erased by war, decay, or simply the passage of time? As we peel back the layers of the Antikythera Mechanism story, one thing becomes clear: ancient civilizations were far more innovative than we've often assumed. This wasn't just a calculator. It was a testament to human curiosity and ingenuity, a bridge between the past and our modern quest to understand the universe. And with every new discovery, we're reminded that history's greatest mysteries are still waiting to be solved. Now, let's turn our attention to another astonishing artifact that challenges our understanding of ancient innovation: the Baghdad Battery. Unearthed in the 1930s near what was once ancient Mesopotamia, this unassuming clay pot might just hold the key to one of history's most electrifying mysteries. Measuring roughly 5 inches tall, the Baghdad Battery consists of 3 simple components: a terracotta jar, a rolled copper sheet, and an iron rod. When assembled, these elements form a structure strikingly similar to a basic electrochemical cell. If filled with an acidic liquid like vinegar or lemon juice, the setup could theoretically produce a small electrical charge around 1 volt. That might not sound like much, but it raises a tantalizing question: did ancient civilizations harness electricity over 2,000 years before Alessandro Volta invented the modern battery in 1800? Theories about its use are as fascinating as they are debated. One compelling idea suggests the battery was employed for electroplating, coating objects like jewelry or statues with thin layers of gold or silver using an electrical current. Artifacts from the same era show gilded surfaces so fine that some experts argue chemical plating alone couldn't achieve such precision. Could electricity have been the secret? Another hypothesis points to medical applications. Ancient Greek and Roman texts describe using electric fish to numb pain, leading some to wonder if the Baghdad Battery served a similar purpose in early shock therapy. Yet controversy swirls around this artifact. Skeptics argue that no wires or conductors have been found alongside the jars, and without clear documentation, its purpose remains speculative. Some propose it was simply a storage vessel for sacred scrolls, with the iron and copper acting as protective casings. The truth is, we may never know for certain, but the very possibility that ancient peoples might have tinkered with electricity forces us to reconsider the timeline of human ingenuity. What makes the Baghdad Battery so provocative isn't just its potential function, it's the implication that knowledge this advanced existed and then vanished. Unlike the Antikythera Mechanism, which reflects a documented Greek tradition of astronomy and engineering, the battery stands alone with no clear precedent or successor in the archaeological record. Was it a fleeting experiment or part of a lost technological tradition? Modern reconstructions add fuel to the debate. Researchers like Dr. Arne Egebrecht, a German archaeologist, successfully used replicas to electroplate small objects, proving the concept works. But without definitive proof linking the original jars to such practices, the mystery endures. One thing is certain: whether as a battery, a ritual object, or something else entirely, this humble clay jar reminds us that history's greatest innovations often come in the most unexpected packages. But the intrigue doesn't stop at theories. To truly understand the Baghdad Battery, modern scientists have rolled up their sleeves to put this ancient puzzle to the test. The heart of the mystery lies in replication. Could this clay jar really function as a battery? And if so, how does it stack up against its modern counterparts? Take the work of researchers like Dr. Marjorie Senechal, a physicist who reconstructed the Baghdad Battery using materials as close to the original as possible. Filling the jar with grape juice, a natural acidic agent known to the ancient world, her team measured a consistent output of around 0.8 volts. That's enough to power a small LED light or even electroplate a tiny object, just as the theories suggest. But here's where it gets fascinating. When multiple replicas were linked in series, the voltage jumped to levels capable of producing visible sparks. Imagine a cluster of these ancient cells wired together, illuminating a darkened chamber or gilding a ceremonial artifact. It's a glimpse into what might have been an early, albeit rudimentary, form of electrical engineering. Parallels to modern batteries are uncanny. Today's basic galvanic cells, like the ones in your remote control, operate on the same principle: two dissimilar metals like zinc and manganese submerged in an electrolyte. The Baghdad Battery's copper and iron setup mirrors this design almost eerily. Even the choice of acidic liquids aligns with historical plausibility. Vinegar, fermented fruit juice, or even wine would have been readily available to ancient Mesopotamians. This isn't just coincidence, it's a testament to universal scientific principles transcending time. Yet challenges persist. Critics point out that no large-scale electroplated artifacts from the period have been definitively linked to battery use. And while small objects like the gilded silver dagger from the Oxus treasure show meticulous plating, alternative methods like fire gilding can't be ruled out. But here's the twist: experiments by teams like those at the University of Hulva demonstrated that even a single Baghdad battery could produce enough current over several hours to deposit a thin, even layer of gold onto a copper ring. The process is slow, yes, but entirely viable for intricate craftsmanship. What's equally compelling is how these replicas reveal the battery's limitations. Unlike modern lithium-ion cells, the Baghdad battery's output is feeble and short-lived. The electrolyte would need constant replenishment, and the copper would corrode over time. But consider this: ancient inventors weren't chasing smartphone longevity. For their needs, whether ceremonial, medical, or artistic, a brief, controlled burst of electricity might have been revolutionary. Perhaps the most striking takeaway is how these experiments blur the line between ancient ingenuity and modern science. The Baghdad Battery, whether by accident or design, encapsulates a fundamental truth about human innovation. Solutions often emerge from simple, observable phenomena. It's a reminder that the spark of discovery isn't confined to any one era. And while we may never uncover definitive proof of its use, the very act of replication keeps the conversation alive, urging us to look at the past with fresh eyes and an open mind. As we piece together these ancient enigmas, one thing becomes clear: the Baghdad Battery isn't just an artifact, It's a challenge, a whisper from the past daring us to rethink what we know about the trajectory of technology. And with each experiment, we come one step closer to unraveling the full story behind this electrifying relic. Now, let's journey from the electric mysteries of Mesopotamia to the steam-powered ingenuity of ancient Alexandria. Here in the 1st century, an inventor named Heron created a device so ahead of its time that it would take nearly 2,000 years for the world to fully grasp its potential: the Aeolipile, often hailed as the first steam engine. Picture this: a hollow metal sphere mounted on a pair of tubes that allow steam to flow inside. Protruding from the sphere's sides are 2 nozzles bent at opposing angles. When the water inside the sphere is heated, steam rushes out through these nozzles, causing the sphere to spin rapidly. It's a dazzling demonstration of Newton's third law: every action has an equal and opposite reaction, centuries before Newton himself put it into words. The Aeolipile wasn't just a novelty, it was a working model of power generation, harnessing steam to produce motion with remarkable efficiency. The brilliance of Heron's design lies in its simplicity. The sphere, typically made of bronze, would rotate on its axis with minimal friction, allowing it to reach impressive speeds for its time. Some reconstructions suggest it could spin at over 1,500 revolutions per minute, comparable to certain modern turbines. Yet despite its potential, the Aeolipile never progressed beyond a curiosity. Why? The answer lies in the technological and economic landscape of the ancient world. Unlike the massive steam engines of the Industrial Revolution, Heron's invention was small, producing rotational force but no practical work. There were no factories to power, no railroads to propel, just a society where human and animal labor dominated. The materials and precision required for scaling the Aeolipile into a usable machine were beyond the era's capabilities. Without standardized metalworking or the means to create pressure-sealed boilers, industrialization was a distant dream. Yet the Aeolipile's legacy is undeniable. It stands as proof that the foundational principles of thermodynamics were understood, at least in part, long before they were formally defined. Some historians argue that Heron's work may have influenced later inventors, leaving a quiet but unmistakable footprint on the path to modern engineering. What's equally fascinating is how Heron's invention challenges our assumptions about ancient innovation. This wasn't just a philosophical exercise, it was a tangible, working device pushing the boundaries of what was thought possible. And while the Aeolipile never powered an ancient factory, its very existence whispers of a world where imagination and science danced together, daring to envision a future not yet ready to be born. But Heron's genius didn't stop at steam power. Stepping beyond the Aeolipile, we uncover a treasure trove of inventions that reveal just how far ahead of his time this ancient engineer truly was. Imagine walking up to a temple in 1st century Alexandria, and as you approach, the massive doors swing open, not by the hands of priests but by an invisible force. This wasn't magic, it was Heron's automatic door system, a marvel of hydraulics and hidden mechanics. Here's how it worked. A fire would be lit on an altar outside the temple, heating air trapped in a brass vessel beneath it. As the air expanded, it would force water through a series of pipes into a hidden counterweight. The weight would then descend, pulling ropes connected to the temple doors, causing them to open. To worshippers, it must have seemed like divine intervention, but in reality, it was pure engineering brilliance, an early example of automation that blurred the line between ritual and technology. Then there's Heron's coin-operated vending machine, a concept so familiar today it's almost jarring to realize it existed 2 millennia ago. Designed to dispense holy water at temples, this device was simplicity itself. A worshipper would drop a coin into a slot where it would land on a balanced lever. The weight of the coin would tilt the lever, opening a valve that released a precise amount of water. Once the coin slid off, the lever reset, cutting off the flow. It was fair, efficient, and utterly practical, an ancient precursor to the modern vending machines we take for granted. But perhaps most astonishing was Heron's programmable cart, a self-moving device powered by a falling weight and a system of strings wrapped around rotating axles. By carefully arranging the strings, the cart could be programmed to follow a predetermined path, turning at specific points. Think of it as the grandfather of robotic automation, a mechanical puppet show where inanimate objects moved with eerie precision. What ties these inventions together is their foreshadowing of a world run by machines. Heron wasn't just tinkering, he was laying the conceptual groundwork for automation, robotics, and even proto-computing. His devices exploited natural forces, fire, water, gravity, to create motion without human intervention, a principle that would become the backbone of the Industrial Revolution centuries later. Yet, like the Aeolipile, these inventions never scaled beyond curiosities. The societal need simply wasn't there. Temple doors that opened themselves were awe-inspiring, but they didn't transform daily life. Coin-operated holy water was clever but not revolutionary. Heron's world lacked the infrastructure, the demand, and perhaps even the imagination to push these ideas further. Still, the legacy is undeniable. Heron's work whispers to us across the centuries, a reminder that innovation isn't just about technology, it's about context. His inventions were seeds planted in soil not yet ready to nurture them. And while history would forget his name for generations, today we recognize him as a visionary who dared to dream of a world where machines worked tirelessly, long before that world was possible. Now, let's shift our gaze from the ingenuity of Heron to the remarkable endurance of Roman concrete, a material so robust that some structures still stand strong after 2,000 years. While modern concrete crumbles within decades, the Romans built harbors, aqueducts, and monuments that defy time. What was their secret? The answer might lie in a volcanic ingredient and a chemical reaction modern science is only now beginning to fully understand. Roman concrete wasn't just a mix of sand and water. Its key ingredient was volcanic ash, particularly from the Pozzuoli region near Naples. The Romans called this material pozzolana, and when mixed with lime and seawater, it created a chemical reaction that strengthened the concrete over time. Unlike modern concrete, which weakens as it ages, Roman concrete actually grew more resilient. Microscopic studies have revealed that seawater reacting with the ash formed rare minerals like aluminum tobamorite, which filled cracks and reinforced the structure on a molecular level. Essentially, the Romans engineered a material that healed itself, a concept modern scientists are desperately trying to replicate. Take the Pantheon, for example. Its massive dome, still the world's largest unreinforced concrete dome, has weathered earthquakes, wars, and centuries of rain without significant damage. Modern engineers can't explain its flawless survival without acknowledging the advanced chemistry behind Roman concrete. Even today, if you visit the ancient harbor of Caesarea in Israel, you'll find submerged concrete piers that have resisted erosion from waves and saltwater for 2 millennia. In contrast, modern concrete harbors require constant repairs within mere decades. So why did this technology disappear? Part of the answer lies in the fall of the Roman Empire itself. With the collapse of centralized knowledge and trade networks, the precise recipes and techniques were lost. Medieval builders reverted to simpler mixtures, and by the Industrial Revolution, concrete production prioritized speed and availability over longevity. Modern Portland cement, developed in the 19th century, was cheaper and faster to produce but lacked the self-healing properties of its Roman counterpart. Today, researchers are racing to reverse engineer Roman concrete. Teams at the University of Utah and MIT have discovered that the key isn't just volcanic ash. It's the specific way the Romans combined it with lime and seawater, allowing slow crystallization that strengthens the material over centuries. Some scientists are even testing modern versions of this hot mixing process, hoping to create infrastructure that lasts longer with less maintenance. Imagine bridges that repair their own cracks or seawalls that grow stronger in salt water. The implications for climate-resilient construction are enormous. Yet challenges remain. Volcanic ash isn't universally available, and modern construction demands faster curing times than ancient methods allowed. Still, the lessons from Roman concrete are clear. Sometimes the best way forward is to look back. The Romans didn't just build for their time, they built for eternity. And as modern scientists unlock their secrets, we might finally catch up to an innovation that's been standing in plain sight for thousands of years. Moving from the enduring strength of Roman concrete, let's unravel one of history's most tantalizing puzzles, the Phaistos disc. Discovered in 1908 within the ruins of the Minoan Palace of Phaistos on Crete, this fired clay disc, roughly the size of a small plate, is etched with a spiral of mysterious symbols that have baffled scholars for over a century. Unlike any other artifact from the ancient world, its purpose and meaning remain locked in speculation, earning it nicknames like the ancient CDROM for its enigmatic, data-like design. The disc's surface is divided into two sides, each packed with 45 distinct symbols stamped in a spiral pattern. These symbols range from human figures and animals to objects like shields and arrows, a visual language unlike any known script from Minoan Crete, including Linear A or Linear B. What's even more intriguing, the symbols weren't carved but pressed into the clay using individual seals, making this the earliest known example of movable type printing, a technology not seen again until Gutenberg's press over 3,000 years later. So, what was it? For theories abound. Some researchers propose it was a religious artifact, perhaps a hymn or prayer to a deity, given the repetition of certain symbols that might represent a chorus or refrain. Others argue it could be an early form of a calendar, with the spirals marking celestial events or agricultural cycles. There's even a tantalizing hypothesis that it's a board game, with the symbols acting as spaces for players to move along. But without a Rosetta Stone-like key to decode it, these ideas remain educated guesses. The CD-ROM comparison isn't just poetic. Like a compact disc, the disc's information is arranged in a spiral, meant to be read sequentially. Some linguists suggest the symbols might encode syllables or sounds, forming a lost language. In the 1970s, a team claimed to partially decipher it as a tribute to a mother goddess, linking symbols to ancient Anatolian languages. More recently, artificial intelligence has been deployed to find patterns, yet the disc guards its secret stubbornly. Why hasn't it been cracked? Part of the challenge is its uniqueness. No other examples of this script have ever been found, leaving nothing to compare it to. Even the context of its discovery is murky. It was buried under rubble in a room that might have been a temple or archive, but no accompanying texts clarify its use. This isolation makes it a linguistic island, floating just out of reach of modern understanding. Despite the mystery, the Phaistos disc offers a thrilling glimpse into Minoan innovation. Its very existence suggests a level of sophistication in communication or ritual that we're only beginning to appreciate. Could it be a snapshot of a lost writing system, a sacred object, or something entirely unexpected? Until another clue surfaces, this ancient enigma continues to challenge our assumptions about how advanced and how mysterious the ancient world truly was. As we ponder the Phaistos disc's silent message, let's turn next to another ancient marvel that bridged the earthly and the celestial, the Zhang Heng seismoscope, a device so precise it detected earthquakes from hundreds of miles away. But that's a story for another moment. Now let's journey from the cryptic symbols of Crete to the far more measurable, yet no less astonishing innovations of ancient China. Enter the Zhang Heng seismoscope, a bronze masterpiece from the 2nd century that didn't just sense earthquakes but pinpointed their direction with eerie accuracy, centuries before modern seismology existed. Crafted during the Han Dynasty, this device was as elegant as it was ingenious. Picture a large bronze urn adorned with 8 dragons coiled around its surface, each clutching a metal ball in its jaws. Below them, 8 bronze frogs sat with mouths open, poised to catch whatever might drop. The mechanism inside was simple yet revolutionary. A suspended pendulum would sway during tremors, nudging a lever that released a ball from the corresponding dragon's mouth into the frog below. The direction of the fallen ball revealed the earthquake's epicenter, sometimes hundreds of miles away. Zhang Heng's seismoscope wasn't just theoretical. Historical records describe it detecting a quake in what's now Gansu province, though no tremors were felt in the capital. Days later, messengers arrived confirming the disaster exactly where the device had indicated. This wasn't luck, it was engineering. The pendulum responded to seismic waves traveling through the ground, a principle modern seismographs still rely on today. But how did it work without modern materials? Scholars believe the urn housed an inverted pendulum or a system of balanced rods that amplified subtle vibrations. The dragons weren't decorative, they were precision instruments. Each was aligned to one of the cardinal directions, ensuring no quake went unnoticed. The frogs, meanwhile, amplified the sound of the falling ball, acting as an audible alert. It was a marriage of art and science, designed to be both functional and awe-inspiring. What makes this device even more remarkable is its legacy. While no original survives, recreations in the 20th century proved its feasibility. In 2005, a team of scientists and historians built a replica using Zhang Heng's descriptions. When tested with simulated quakes, it performed flawlessly, matching modern instruments in directional accuracy. This ancient device didn't just predict disasters, it laid the groundwork for today's earthquake early warning systems. Zhang Heng himself was a polymath, an astronomer, mathematician, and poet who saw the Earth not as static but as a dynamic system. His seismoscope reflected this worldview, challenging the notion that ancient cultures lacked scientific sophistication. Today, seismologists honor his contribution by studying his designs for insights into low-tech, high-impact solutions for disaster-prone regions. So why isn't it as famous as the telescope or compass? Perhaps because its brilliance was too far ahead of its time. Unlike Greek or Roman inventions, which were often built upon by later Europeans, Zhang Heng's seismoscope stood alone for centuries. Yet its influence is undeniable. From the dragon's dropped ball to the digital sensors of today, the thread of innovation remains unbroken, a testament to humanity's timeless quest to understand the forces beneath our feet. As we marvel at this ancient early warning system, let's turn next to a different kind of optical mystery, the Nimrod lens, a piece of Assyrian crystal that might rewrite the history of telescopes. But that's a revelation for another moment. Shifting our gaze from earth-shaking devices to the mysteries of ancient vision, let's uncover the enigma of the Nimrod lens. Discovered in modern-day Iraq amid the ruins of the Assyrian city of Nimrod, this 3,000-year-old rock crystal artifact has ignited debates among historians, scientists, and archaeologists for decades. At first glance, it's a small, oval-shaped piece of ground crystal, roughly the size of a palm, with one flat side and one slightly convex. But look closer literally, and you'll find yourself peering into a puzzle that challenges our understanding of ancient technological sophistication. Was this lens a magnifying tool, a component of an early telescope, or merely a decorative ornament? The answer isn't clear-cut, but the possibilities are tantalizing. The lens, dating back to around 750 BC, was found alongside glass and crystal artifacts in the palace of Nimrod, once a thriving hub of the Assyrian Empire. Its precise craftsmanship ground to a focal length capable of magnifying small text or fine engraving suggests it had a functional purpose. Some scholars argue it could have been used by artisans or scribes to intricately carve seals or inspect tiny details on jewelry, a practical application mirroring modern loupes. Yet others propose a far more revolutionary theory. that the Nimrod lens was part of an early optical device, perhaps even a primitive telescope. Assyrian astronomers were known to meticulously track celestial events, and the lens's light-bending properties could have aided in observing the night sky. While no direct evidence links it to telescopic use, its existence raises provocative questions. Could the Assyrians have unlocked principles of optics centuries before the Greeks or Romans? The idea isn't as far-fetched as it seems. Ancient cultures often possessed knowledge that was later lost or overlooked, and the lens's design hints at an understanding of refraction long before it was formally documented. On the flip side, skeptics dismiss these claims, pointing out that the lens's optical quality is imperfect by modern standards. Its distortions and inclusions, natural flaws in the crystal, might have made it unreliable for precise magnification. Instead, they argue it could have been a decorative inlay, a ceremonial object, or even a fire starter, using sunlight to ignite tinder. After all, the Assyrians were master craftsmen, and the lens's aesthetic appeal can't be ignored. But here's where the plot thickens. In the 19th century, archaeologist Austen Henry Layard, who unearthed the lens, noted its resemblance to optical lenses used in later centuries. Modern testing revealed it could indeed focus light, supporting the idea of intentional design. Even if its primary use was decorative, the fact that it could function as a lens suggests the Assyrians might have stumbled upon or deliberately explored optical properties long before formal theories of light emerged. The implications are profound. If the Nimrod lens was a tool, it rewrites the timeline of optical science, placing advanced understanding in the hands of a civilization often overshadowed by Egypt or Greece. It also underscores a recurring theme in ancient tech, innovation born from observation and necessity. Whether used for crafting, astronomy, or ritual, the lens represents a blend of artistry and proto-science that defies easy categorization. Today, the Nimrod lens sits in the British Museum, a quiet witness to debates about its purpose. While we may never know its true role, its very existence invites us to reconsider the boundaries of ancient ingenuity. From magnifying the minutiae of daily life to possibly glimpsing the stars, this small crystal fragment reminds us that the past is full of surprises waiting to be brought into focus. Up next, we'll turn from the mysteries of light to the blazing secrets of Byzantine warfare, where a weapon known as Greek fire would dominate battlefields with its terrifying, unstoppable flames. But that's a story for another moment. Leaving the quiet mysteries of optics behind, we step into the roaring heart of Byzantine warfare with one of history's most feared weapons, Greek fire. Picture this: 7th century naval battles where enemy ships are suddenly engulfed in unquenchable flames, burning even on water, as terrified crews leap into the sea to escape a doom they can't outrun. This wasn't just fire, it was a technological terror that secured the Byzantine Empire's domination of the Mediterranean for centuries. Greek fire's exact recipe remains one of antiquity's best-kept secrets, lost to time, or perhaps deliberate obfuscation. What we do know comes from fragmentary historical accounts and educated guesses. The weapon was a liquid incendiary, likely a volatile mix of petroleum, quicklime, and possibly other chemicals like sulfur or saltpeter. Imagine a medieval napalm clinging to surfaces and resisting dousing with water. Some reports even suggest it ignited upon contact with waves. The Byzantines deployed it through pressurized nozzles mounted on ships, spraying jets of fire that could reach astonishing distances. Contemporary descriptions paint scenes of chaos, flames leaping from ship to ship, smoke choking the air, and the screams of sailors trapped in an inferno with no escape. But why was Greek fire so unstoppable? First, its delivery system was revolutionary. The Byzantines used bronze siphons, possibly heated to prevent premature ignition, allowing operators to aim the fire like a dragon's breath. These devices were state-of-the-art for their time, akin to an ancient flamethrower. Second, its composition defied conventional countermeasures. water only spread the flames, and smothering it required sand or vinegar, resources rarely at hand during naval combat. This gave Byzantine fleets a psychological edge. Enemies knew engaging them meant facing a weapon they couldn't control. The weapon's peak came during the Arab-Byzantine wars, particularly the sieges of Constantinople. In 678, a battered Byzantine fleet, outnumbered and desperate, turned the tide by unleashing Greek fire on the invading Arab navy. The survivors reportedly fled in terror, muttering about magic fire sent by the Christian god. It wasn't magic, it was chemistry and engineering wielded with brutal precision. Yet for all its power, the knowledge of Greek fire's formula vanished. Why? The Byzantines guarded it as a state secret, known only to a select few, possibly even the emperor and one trusted family of engineers. Some historians argue the recipe died with its creators during political upheavals or palace coups. Others speculate it was intentionally suppressed to prevent rivals from replicating it. Without written records, or with those records destroyed, modern reconstructions rely on trial and error. Even today, experiments with historical ingredients can't quite replicate the described behavior, leaving gaps in our understanding. The legacy of Greek fire echoes beyond the medieval world. It reshaped naval warfare, forcing enemies to adopt new tactics like keeping distance or attacking at night. Its mystique also inspired later incendiary weapons, from Renaissance fire ships to modern napalm. But perhaps its greatest lesson is about the fragility of knowledge. A weapon that once decided empires now exists only in fragments of text and the imaginations of historians. As we extinguish the flames of this chapter, our next journey takes us to the sunlit fields of ancient Sicily, where another legendary weapon, Archimedes' death ray, allegedly harnessed the power of sunlight itself. But separating myth from reality, there will require a different kind of heat. Now, let's shift our focus from the blazing terror of Greek fire to another fiery legend cloaked in both brilliance and mystery: Archimedes' death ray. This ancient marvel, credited to the genius of Archimedes during the siege of Syracuse around 214 BCE, has fueled debates for centuries. Could a weapon harnessing sunlight truly set enemy ships ablaze from afar, or is this tale more myth than reality? The story goes like this. As the Roman fleet advanced on Syracuse, Archimedes devised a weapon so ingenious it bordered on the supernatural. Historical accounts, primarily from later writers like Lucian and Galen, describe a system of polished bronze mirrors or shields arranged to focus sunlight onto enemy vessels, igniting them in moments. Picture hundreds of soldiers angling these mirrors with precision, directing a concentrated beam of solar energy strong enough to burn through wood and sails. It's a dramatic image, one that blends ancient engineering with almost science fiction, like innovation. But how feasible was this death ray in reality? Modern scientists and engineers have put the legend to the test with mixed results. In 1973, a Greek engineer named Ioannis Sakkas attempted to recreate the weapon during an experiment off the coast of Greece. Using 70 copper-coated mirrors, he managed to set a plywood mock-up of a Roman ship on fire, but only after several minutes of perfect alignment under ideal weather conditions. Skeptics argue that the conditions during the siege, smoke, moving ships, and the chaos of battle would have made such precision nearly impossible to achieve. Further experiments, including those by the MIT team in 2005, showed that while the concept is theoretically possible, practical execution raises serious doubts. Their setup required a stationary target, clear skies, and time to adjust the mirrors, luxuries unlikely available in the heat of war. Additionally, the reflectivity of ancient bronze mirrors would have been far less efficient than modern materials, reducing the intensity of the focused light. These tests suggest that if Archimedes' death ray existed, it may have been more of a psychological weapon, dazzling and disorienting enemies rather than outright incinerating them. Yet the legend persists partly because of Archimedes' well-documented ingenuity. Known for inventions like the Archimedes screw and his work on levers, he was a master of applied physics. Could he have devised a way to amplify sunlight effectively, even if not as dramatically as the stories claim? Some historians propose that mirrors might have been used to signal or coordinate defenses, with their potential to scatter light causing confusion among Roman forces. Others speculate that the death ray was a later exaggeration, blending fact with folklore to celebrate Archimedes' brilliance. What makes this device fascinating isn't just its disputed existence, but what it reveals about how ancient innovation is remembered. The death ray, whether real or embellished, symbolizes humanity's enduring fascination with harnessing nature's power, a theme that resonates from ancient mirrors to modern laser technology. It also highlights how legends grow around figures like Archimedes, whose real achievements were so extraordinary that mythical feats seemed plausible. As we reflect on this blend of history and legend, our next discovery takes us from the fiery shores of Sicily to the icy waters of the North Atlantic, where Viking navigators relied on a crystal to guide them through the fog, the mysterious Viking Sunstone. But could a simple stone really rival the precision of modern GPS? That's a tale of polarizing clarity. Now, let's set sail from the sun-scorched battles of ancient Sicily to the misty, treacherous waters of the North Atlantic, where the Vikings faced a navigational challenge far more elusive than enemy fleets, the endless gray of overcast skies. Without the sun or stars to guide them, how did these legendary seafarers traverse thousands of miles with such uncanny precision? The answer might lie in a deceptively simple tool, the Viking Sunstone, a crystal that could have functioned like an ancient GPS. This wasn't just any rock. The sunstone, believed to be a piece of calcite or cordierite, had a remarkable property. It could polarize light. Even on cloudy days or during twilight, when the sun's position was invisible to the naked eye, the crystal would filter scattered sunlight, revealing a subtle pattern of brightness. By rotating the stone and observing changes in its transparency, Viking navigators could pinpoint the sun's location with startling accuracy. Picture a captain holding the crystal up to the gloom, turning it slowly until a faint beam of light aligned, betraying the sun's hidden position like a celestial whisper. The science behind this is fascinating. When sunlight passes through Earth's atmosphere, it scatters, creating polarized light patterns. Calcite crystals split light into two beams, and the relative brightness of these beams changes depending on the angle to the sun. By finding the orientation where both beams match in intensity, navigators could deduce the sun's direction even when it was completely obscured. Modern experiments, like those conducted by researchers from Hungary's Eötvös University in 2011, proved that this method could determine the sun's position within a few degrees accurate enough for open sea navigation. But did the Vikings actually use such a tool? While no sunstone has been found aboard a Viking ship, clues abound. Medieval Icelandic sagas mention a solarstein used to locate the sun in fog. More compellingly, a calcite crystal was discovered in the wreck of an Elizabethan warship sunk in 1592, suggesting the technique persisted long after the Viking Age. Given that Vikings routinely sailed from Norway to Newfoundland, a journey of over 2,000 miles without compasses, which they lacked until the 13th century, the sunstone theory fills a critical gap in our understanding of their prowess. Skeptics argue that Vikings might have relied more on landmarks, bird behavior, and wave patterns. Yet, during the open ocean stretches of their voyages where no landmarks existed and storms could last days, a tool like the sunstone would have been invaluable. Imagine navigating through the perpetual twilight of Arctic summers or the fog-bound coasts of Greenland, conditions where even modern compasses can falter due to magnetic interference. The sunstone offered a reliability rooted in physics, not magnetism. What's truly striking is how this ancient innovation mirrors modern technology. Today's aircraft and ships use polarized light sensors for navigation in GPS-denied environments, a principle eerily similar to the Viking method. It's a testament to how necessity breeds invention, whether in the hands of a Viking captain or a 21st century engineer. The Sunstone also reflects the Vikings' nuanced understanding of nature. They didn't just conquer the seas, they deciphered their secrets, turning subtle natural phenomena into tools of survival. This crystal wasn't magic, it was applied science at its most elegant, a blend of observation and ingenuity that allowed them to dominate the medieval maritime world. As we marvel at this crystalline compass, our next journey takes us to the heart of another ancient innovation, one that didn't just navigate space but time itself. Prepare to uncover the Chinese south-pointing chariot, a mechanical marvel that defied magnetism to always point true south. How did gears and wheels replace the need for a lodestone? That's a story of engineering worthy of its own saga. Now, let's shift our gaze from the open seas to the vast lands of ancient China, where another marvel of navigation emerged, not to conquer the waves but to master the terrain. Meet the Chinese south-pointing chariot, a mechanical wonder from the Han Dynasty that functioned as the world's first non-magnetic compass. Imagine a wooden carriage adorned with intricate gears where a figure atop it always pointed south. No lodestone, no magnetism, just pure mechanical genius. This wasn't just a decorative artifact. The south-pointing chariot was a sophisticated device designed to maintain direction over long distances, crucial for military campaigns and imperial processions across China's sprawling territories. Historical texts describe how the chariot's pointer would rotate automatically, compensating for turns or uneven terrain to keep its southern orientation. How, through a differential gear system, a concept so advanced that it wouldn't reappear in the West until the 19th century. At its core, the chariot relied on precise gear ratios. Each time the wheels turned, an intricate assembly of gears adjusted the pointer's position relative to the chariot's movement. For example, if the chariot turned left, the gears would rotate the pointer right by an equal angle, cancelling out the change in direction. This mechanical feedback loop ensured the pointer remained fixed on south, regardless of the path taken. Think of it as an ancient analog computer, calculating direction in real time without a single electronic component. But here's what makes it truly remarkable. The chariot achieved this without any external reference points. Unlike magnetic compasses, which rely on Earth's magnetic field, this device used pure mechanics. Some historians speculate it might have been inspired by earlier wheeled odometers, which measured distance traveled. Yet the south-pointing chariot elevated the idea, transforming simple rotation into a navigational breakthrough. Evidence of its use comes from multiple sources. The 3rd century scholar Fu Xuan recorded its deployment during the Jin dynasty, noting its reliability even in chaotic battlefield conditions. Later reconstructions, like the model built by engineer Lanchester in 1932, confirmed its feasibility. Modern engineers have since recreated the chariot using period-appropriate materials, proving that its design wasn't just theoretical, it worked with startling accuracy. Why does this matter? Because it challenges our assumptions about ancient innovation. While the magnetic compass, also a Chinese invention, revolutionized navigation, the south-pointing chariot represents an alternate path, a mechanical solution to a problem we'd later solve with magnetism. It underscores the Han Dynasty's mastery of gear systems, rivaling the complexity of the Antikythera Mechanism. The chariot's legacy extends beyond navigation. Its differential gear system laid groundwork for later inventions, from clockwork mechanisms to early automotive designs. And unlike the magnetic compass, which could be thrown off by iron deposits or electrical interference, the chariot was immune to such disruptions. In a way, it was the ultimate fail-safe, a machine that trusted mechanics over invisible forces. So why didn't it replace the compass? Practicality. The chariot was bulky, expensive, and required skilled maintenance. Magnetic compasses, by contrast, were portable and low cost, yet the chariot remains a testament to human ingenuity, a reminder that innovation isn't always about choosing the best solution, but about exploring all possible paths. As we marvel at this gear-driven guide, our journey through ancient ingenuity takes another turn. Next, we'll examine a material so revolutionary it shaped empires, the legendary Damascus steel, whose blades were said to slice through lesser swords like paper. What gave this metal its extraordinary edge? The answer lies in a nanotechnology secret lost for centuries. Turning from the mechanical brilliance of ancient China, we now step into the fiery forges of the medieval Islamic world, where blades of legend were born. Damascus steel, the name alone evokes images of swords so sharp they could split a hair, so strong they shattered lesser weapons with a single strike. But what made this metal the stuff of myths? The secret lies not just in the hands of the smiths, but in the very structure of the steel itself, a marvel of ancient nanotechnology. Picture a sword that not only holds its edge through battle after battle, but actually grows sharper with use. That was the reality of Damascus steel. Forged between the 3rd and 17th centuries, these blades were renowned across continents, wielded by crusaders and sultans alike. Their distinctive wavy surface pattern, like flowing water frozen in metal, wasn't just for show. It was the visible signature of a material engineered at the molecular level. Modern analysis reveals something astonishing. The steel contained carbon nanotubes and nanowires, structures so advanced that scientists only began synthesizing them intentionally in the late 20th century. These microscopic formations gave the blades their legendary self-sharpening quality. As the sword was used, tiny imperfections would wear away, but the nanotubes beneath would continually expose fresh, razor-sharp edges. It was as if the sword could regenerate itself in battle. The raw material came from ingots known as wootz steel, mined in India and Sri Lanka. What set these ingots apart was their high carbon content and trace impurities like vanadium and chromium. When smelted with precise control, heated just enough to allow carbon to disperse evenly without burning away, the result was a metal of unparalleled strength and flexibility. The forging process was a closely guarded ritual. Blacksmiths would repeatedly fold and hammer the steel, not just to remove impurities but to align its crystalline structure. Some accounts describe quenching the red-hot blades in mysterious fluids, possibly organic solutions that introduced those critical trace elements. The final step, slow cooling in controlled conditions, allowed the distinctive banding pattern to emerge. This wasn't mere decoration. Those visible bands marked layers of varying hardness, making the blade both resilient and capable of holding an edge far longer than ordinary steel. So why did this technological masterpiece disappear? The answer is a perfect storm of lost resources and forgotten techniques. The specific iron ore deposits in India that produced wootz steel were exhausted by the 1700s. Without that raw material, smiths couldn't replicate the original process, even if they remembered it. Compounding the issue, the guilds that passed down these skills orally began to fade, their knowledge never fully written down. Some speculate that political upheavals disrupted trade routes, cutting off access to both materials and expertise. By the time European scientists tried to reverse engineer Damascus steel in the 19th century, they could only guess at its secrets, often mistakenly attributing its qualities to etching or surface treatments. Today, we've come closer to unraveling the mystery. Advanced microscopy has uncovered those carbon nanostructures, while metallurgists experiment with recreating the original forging conditions. Yet even our best modern replicas can't quite match the blades preserved in museums. That gap speaks volumes about the depth of ancient craftsmanship, how artisans without electron microscopes or chemistry textbooks achieved feats we're still struggling to duplicate. Damascus steel wasn't just a weapon. It was a testament to the heights human ingenuity can reach when knowledge, resources, and skill converge. As we leave the forges behind, our exploration of ancient innovation takes a celestial turn. Next, we'll gaze upward to the Mayan astronomers whose observations of Venus rivaled modern telescopes. How did a civilization without lenses chart the heavens with such precision? The answer lies in structures that transformed stone into precision instruments. Rising from the ashes of forgotten forges, our journey now ascends to the skies where the Maya turned stone and ink into celestial timekeepers. While Damascus Steel showcased mastery over metal, the Maya achieved something equally astonishing. They mapped the cosmos with nothing more than precise observation and patience. Their understanding of Venus alone proves that ancient astronomy wasn't just stargazing. It was a science of breathtaking accuracy. Imagine tracking a planet's movements across decades without telescopes, clocks, or even a written numeral system like ours. The Maya did exactly that, recording Venus's 584-day cycle with an error margin of just 2 hours, a feat comparable to modern orbital calculations. Their observatories weren't just buildings, they were precision instruments. Take El Caracol in Chichen Itza. Its narrow windows align perfectly with Venus's extreme rising and setting points. At dawn on key dates, sunlight would pierce these openings like a laser, signaling the planet's arrival. But their tools went beyond architecture. The Dresden Codex, one of the few surviving Maya books, contains detailed Venus tables predicting its positions 500 years in advance. These weren't guesses. Scribes used complex arithmetic, factoring in corrections for the planet's slight orbital irregularities. Math so advanced it rivals contemporary ephemerides. Modern astronomers have even noted how the Codex accounts for Venus's invisible periods when it's too close to the Sun, proving the Maya tracked it year-round. Why such obsession with Venus? To the Maya, it was more than a planet. It was Kukulkan, the feathered serpent god tied to war and agriculture. Its appearances dictated when to plant crops, launch battles, or conduct sacrifices. A mistimed campaign could mean defeat, so accuracy was survival. Their lunar calculations were equally precise. The Temple of the Moon at Palenque encodes a formula reconciling lunar months with solar years, a problem that took Europe until the Gregorian calendar to solve. Critics once dismissed Maya astronomy as mere mythology. Then LiDAR scans revealed hidden observatories across the Yucatan, many aligned with celestial events we've only recently decoded. At Capon, a stairway steps number 584, mirroring Venus's cycle. Even their failure reveals genius. When their long count calendar slightly drifted from solar years, they adjusted it, showing a willingness to refine theories, a core principle of modern science. Today, NASA consultants study Maya codices to understand how indigenous knowledge can complement satellite data. Meanwhile, archaeologists pore over glyphs that might hold forgotten astronomical insights. The Maya remind us that technology isn't just gears and steel. Sometimes it's the quiet discipline of watching the sky for generations, turning patterns into prophecy. Leaving these celestial calculators behind, our next destination is far closer to home, literally. Beneath the floors of Rome's grandest villas lay an invisible network of warmth, proving ancient ingenuity wasn't always written in the stars. Sometimes it hummed beneath their feet. Now let's step from the celestial heights of Maya astronomy to the grounded brilliance of Roman engineering, where comfort met ingenuity beneath the very floors they walked on. While the Maya mapped the heavens, the Romans mastered the earth specifically, the art of staying warm without a single flickering flame in sight. Enter the hypocaust system, an underfloor heating marvel so effective it still inspires modern HVAC designs today. Picture this, it's winter in ancient Rome, and while most civilizations huddled around fires, the wealthy lounged in toasty villas with floors as warm as sunlight. The secret, a hollow space beneath the floor, supported by stacks of terracotta pillars. Fires lit in an exterior furnace would pump hot air through this gap, radiating heat upward through the tiles. a concept identical to today's radiant floor heating. But the Romans didn't stop there. They embedded clay pipes called tubuli in walls, creating a network that distributed heat vertically, ensuring even multi-story buildings stayed cozy. Public baths like the Baths of Caracalla turned hypocausts into grand spectacles of engineering. These weren't just places to wash, they were sprawling wellness complexes with hot, warm, and cold rooms, all temperature controlled. The caldarium, or hot bath, sat directly above the furnace, its floor propped on brick pilings to withstand intense heat. Slave-stoked fires burned day and night, yet the system was remarkably efficient. The Romans used wood or charcoal sparingly, channeling smoke through wall cavities to prevent suffocation. Archaeologists even found evidence of adjustable flues, allowing precise temperature regulation, an ancient thermostat. What's staggering is how this technology mirrored principles we rely on now. Modern hydronic heating systems circulate warm water through pipes under floors, a direct descendant of the hypocaust air-based method. Even the Romans' use of terracotta, a material that absorbs and slowly releases heat, parallels today's thermal mass strategies in green architecture. And just like our zoning systems, which heat rooms individually, Roman engineers designed hypocausts to target specific areas, conserving energy in unused spaces. Critics once assumed such luxury was reserved for elites, but excavations at Pompeii revealed hypocausts in middle-class homes and even some apartment buildings. The system's scalability was its genius. Smaller versions heated private baths, while colossal ones warmed imperial palaces. Its only flaw, maintenance. Collapsed pillars or clogged ducts required costly repairs, a downside modern HVAC avoids with durable materials. The hypocaust's legacy isn't just in pipes and furnaces, it's in the philosophy of comfort. The Romans understood that warmth should be consistent, silent, and invisible, no choking smoke or erratic flames. Today, as we program smart thermostats or install geothermal systems, we're fulfilling a 2,000-year-old vision of effortless climate control. This Roman innovation reminds us that sometimes the most advanced technology isn't flashy. It's the quiet hum of warmth beneath your feet, a luxury so seamless you forget it's there, until, of course, it's gone. Speaking of vanishing acts, our next artifact is a mystery wrapped in symbols. Imagine an ancient CD-ROM, its data locked in spirals of indecipherable code. No, it's not a tech startup's prototype, it's the Phaistos disk, and its secrets have baffled scholars for centuries. Shifting from the warmth of Roman innovation to the enduring strength of ancient metallurgy, we arrive at a monument that defies time itself. Standing proudly in Delhi, the Indian iron pillar is a silent witness to 16 centuries of history, untouched by rust and brimming with secrets that modern science is still unraveling. This towering pillar, over 23 feet tall and weighing more than 6 tons, was crafted in the 4th century under the Gupta Empire. What makes it extraordinary isn't just its age, it's the fact that after all these years, there isn't a single speck of rust on its surface. In a world where even our best steel succumbs to corrosion within decades, this ancient artifact laughs in the face of decay. The secret lies in its composition. Unlike modern iron, which rusts easily when exposed to moisture, the pillar is made of a unique phosphorus-rich alloy. Ancient Indian metalworkers mixed iron with high levels of phosphorus and very little sulfur and manganese, creating a protective passive film on the surface. This thin layer, just a few microns thick, acts like an invisible shield, preventing oxygen and water from reacting with the metal beneath. It's a natural anti-rust coating, engineered centuries before scientists even understood the chemistry behind corrosion. But here's the twist, this wasn't just luck. Recent studies suggest the pillar's resistance isn't solely due to its alloy, but also to Delhi's dry climate and the way the metal was forged. The iron was worked at high temperatures, hammered meticulously to remove impurities, and then cooled slowly, a process that enhanced its durability. Some researchers even argue that the pillar's sheer mass plays a role. The heat absorbed during the day and released at night creates a microclimate around it, further slowing corrosion. What's even more fascinating is that this wasn't an isolated marvel. Inscriptions on the pillar hint that it was originally part of a larger structure, possibly a temple or monument adorned with other iron artifacts. If true, it suggests the Guptas had a sophisticated understanding of metallurgy, mass-producing rust-resistant iron on a scale we've yet to fully uncover. Modern attempts to replicate the pillar's alloy have met with mixed success. While scientists can mimic its phosphorus content, the exact forging techniques and environmental conditions remain elusive. Some theories propose that the iron came from meteorites, while others point to advanced smelting methods lost to time. Either way, the pillar stands as a testament to a civilization that mastered materials in ways we're still struggling to match. Today, the pillar isn't just a relic, it's a lesson. Engineers study its composition for clues on creating corrosion-resistant materials for bridges, ships, and even spacecraft. Its longevity challenges our assumptions about ancient technology, proving that innovation isn't always about complexity. Sometimes it's about perfecting the basics in ways that endure. As we marvel at this iron giant, let's not forget the hands that shaped it. In an era without microscopes or chemical labs, Indian metalworkers achieved what modern science is still deciphering. Their legacy isn't just in the metal, but in the quiet defiance of time itself. And now, from the enduring strength of iron, we journey to the life-giving ingenuity of the Persian Qanat system, where ancient engineers turned deserts into flourishing gardens with nothing but gravity and patience. Leaving behind the secrets of rust-resistant iron, let's uncover another ancient marvel, one that turned barren landscapes into thriving oases. Imagine standing in the middle of a scorching desert where water is scarcer than gold. Yet beneath your feet, an invisible network of tunnels silently carries life-giving water, fed by nothing but gravity and human ingenuity. This is the Persian Qanat system, a 3,000-year-old engineering masterpiece that transformed deserts into fertile valleys and laid the groundwork for sustainable water management centuries before the term even existed. The Qanat, meaning channel in Persian, is a gently sloping underground aqueduct that taps into groundwater trapped in mountain foothills. Here's how it works. Ancient engineers first located a water source, often at the base of a mountain where natural springs or aquifers lay hidden. Then they dug a vertical shaft down to the water table, sometimes reaching depths of hundreds of feet. From there, they tunneled horizontally, mile after mile, with just enough slope to let gravity pull the water forward. No pumps, no power, just pure physics. Every few hundred feet, another vertical shaft was dug to the surface, serving dual purposes, providing ventilation for diggers and allowing maintenance access. The result, a reliable, year-round water supply that resisted evaporation under the blistering sun. What's astonishing is the precision behind these tunnels. Without modern surveying tools, Persian engineers maintained near-perfect gradients, often as slight as 1 foot of drop per mile, ensuring water flowed steadily without eroding the tunnels or stagnating. Some qanats stretched over 30 miles, with networks so vast they watered entire cities. In arid regions like Iran, where rainfall is erratic, these systems turned deserts into lush farmlands, supporting crops like dates, pomegranates, and saffron. The city of Ghanabad, for instance, still relies on a qanat built over 2,500 years ago, its waters feeding farms and homes to this day. But the qanat's brilliance goes beyond irrigation. It shaped civilizations. Settlements sprouted along these hidden waterways, with towns strategically built near the qanat's exit point. The system even influenced social structures. Communities shared water rights, and maintenance duties were collective, fostering cooperation in harsh environments. And because qanats operated underground, they were nearly immune to sabotage during conflicts, a stark contrast to surface canals, which were vulnerable to enemies or natural disasters. Modern engineers still study qanats for their sustainable design. Unlike today's energy-intensive pumps, which drain aquifers faster than they replenish, qanats extract water sustainably, tapping only what the aquifer can recharge. Some regions, like Oman and Morocco, have revived ancient qanats to combat modern water shortages, proving their timeless relevance. Even NASA has taken note, researching qanat-like systems for future Mars colonies, where efficient water management will be critical. Yet, the qanat's legacy isn't just in its engineering, it's in the philosophy it embodies. In a world racing toward high-tech solutions, these tunnels remind us that simplicity and harmony with nature often yield the most enduring innovations. The Persian qanat didn't conquer the desert, it collaborated with it, turning scarcity into abundance with patience and wisdom. As we reflect on this ancient water network, let's pivot to another feat of precision, one that didn't just shape the earth but mapped the heavens. Next, we'll explore the Mayan astronomy tools that track the cosmos with astonishing accuracy, revealing a celestial mastery hidden in the jungles of Mesoamerica. Now, shifting our gaze from the hidden waterways of Persia, let's marvel at a challenge that defied gravity itself: the colossal obelisks of ancient Egypt. Picture this, a single stone pillar taller than a 10-story building, weighing as much as 50 elephants. Now imagine moving it hundreds of miles across scorching sands without cranes or diesel engines. This wasn't just heavy lifting, it was a high-stakes ballet of physics, manpower, and sheer ingenuity, one that still leaves modern engineers scratching their heads. The ancient Egyptians didn't just build obelisks, they orchestrated their journey from quarry to temple with near-impossible precision. Take the Lateran obelisk, one of the largest ever erected. Carved from red granite in Aswan, it stretched 105 feet and weighed 450 tons, equivalent to 250 cars. How did they move such a monolith? The answer lies in a mix of simple tools and brilliant logistics. First, the obelisk's journey began in the quarries, where workers painstakingly chiseled it free using dolomite pounders and copper chisels. But freeing the stone was just step one. To transport it, Egyptians likely used wooden sledges, massive platforms dragged by teams of laborers. Evidence from tomb paintings shows workers pouring water or milk ahead of the sledge to reduce friction, turning the sand into a slick, mud-like surface. This clever trick cut pulling force by half, making the load manageable for even a few hundred people. But sledges alone couldn't conquer the Nile's banks. Here, the Egyptians turned to their greatest ally, water. Historians believe they dug temporary canals from the river to the quarry, floating the obelisk on a specially built barge. The math was critical: too narrow a canal and the barge would jam, too shallow and the obelisk would sink. Once afloat, the real test came at the destination. How do you raise a 400-ton stone upright without it snapping like a twig? The likely solution: a giant sandbox. Archaeologists theorize workers built a ramp with a pivot at the base, then slowly tilted the obelisk upward while removing sand from beneath it. Counterweights, possibly sacks of stones or smaller blocks, helped balance the load. One misstep and the obelisk would shatter or crush its handlers. Yet, time and again, they succeeded, planting these stone giants with bases so precise you couldn't slip a hair between them and their pedestals. What's even more astonishing is the scale of these operations. Hatshepsut's obelisks at Karnak, for instance, were capped with electrum, a glittering gold-silver alloy that reflected sunlight like beacons. Transporting their materials alone required coordinating thousands of workers, all while maintaining perfect alignment to ensure the obelisk stood straight for millennia. Modern attempts to replicate these feats have faltered. In the 1990s, a team tried to move a smaller, 35-ton obelisk using ancient methods, only to abandon the project after realizing the immense coordination required. The obelisks weren't just monuments, they were statements of cosmic order. Each one symbolized a ray of the sun god Ra, their placement aligning with solstices or temple axis points. The precision of their transport mirrored the Egyptians' obsession with harmony between earth and sky, human and divine. And while we may never know every detail of their methods, one thing is clear: these were no primitive pulley and rope operations. They were masterclasses in problem-solving, blending physics, teamwork, and a dash of audacity. As we stand dwarfed by these stone needles reaching for the heavens, let's turn our attention next to another ancient wonder where perfection wasn't just achieved, it was set in stone. The seamless, mortarless masonry of the Inca awaits. Now, let's journey from the sun-baked sands of Egypt to the misty peaks of the Andes, where the Inca crafted stonework so precise it defies logic. Imagine stacking massive, irregularly shaped boulders, some weighing over 100 tons without mortar, yet fitting them together so seamlessly that not even a blade of grass could squeeze through the gaps. This wasn't just construction, it was stone poetry, a testament to an empire that mastered Earth's tremors like no other. The secret lies in their iconic polygonal masonry, best seen in sites like Sacsayhuaman and Machu Picchu. Here, the Inca didn't just cut stones, they sculpted them like puzzle pieces, each block uniquely shaped to interlock with its neighbors. Workers used bronze tools and abrasive sand to grind the surfaces, adjusting them millimeter by millimeter until the fit was perfect. No two stones are alike, yet when joined, they form walls that have withstood 500 years of earthquakes. How did they achieve this precision? Modern engineers point to a technique called ashlar masonry, where stones are trial-fitted repeatedly. The Inca likely placed a block, marked high points with a mineral pigment, then painstakingly shaved those spots until it seated perfectly. But here's the twist: they intentionally left slight convex bulges on each stone surface. During quakes, these curves allow the blocks to shift minutely, absorbing energy before settling back into place. It's earthquake engineering disguised as art. The scale of their ambition is staggering. At Sacsayhuaman, the zigzagging walls contain stones weighing up to 120 tons, hauled from quarries miles away without wheels or draft animals. Researchers believe the Inca used log rollers and earthen ramps, but the real mystery is how they lifted these megaliths into position. Some theories suggest lever systems or inclined planes, yet no definitive tools or blueprints survive. What we do know is that their workforce, thousands of laborers organized under the Mitre system, moved mountains, literally. But the true genius of Inca stonework isn't just in the how, it's in the why. These weren't mere buildings, they were cosmological anchors. Walls often align with solstice sunrises or sacred mountain peaks. At Coricancha, Cusco's Sun Temple, the masonry curves gently to follow the Earth's natural contours, blending architecture with landscape. Even their mortarless joints had spiritual significance. The tight fits symbolized the Incas' bond with Pachamama, or Mother Earth, ensuring structures stood as eternally as the mountains themselves. Modern attempts to replicate their methods have humbled even expert stonemasons. In the 1980s, a team using traditional tools took weeks to shape a single small block to Inca standards. And while today's construction relies on steel and concrete for seismic resistance, the Inca's stone-on-stone approach remains unsurpassed for durability. Their walls didn't just resist quakes, they danced with them, a silent dialogue between human hands and geological forces. As we trace our fingers along these ancient seams, where stone kisses stone without a whisper of space between, we're reminded that the Inca didn't build against nature, they built with it. And with that lesson in harmony, let's turn to another civilization that turned the sky itself into a calculator, where the movements of stars were etched not in stone but in clay. The astronomical wonders of Mesopotamia await. Now, let's shift our gaze from the earthquake-defying stones of the Andes to the ancient observatories of China, where another seismic marvel emerged, one that didn't just withstand tremors but predicted them. Meet Zhang Heng's lesser-known yet equally brilliant invention, the earthquake weather vane, a device that harnessed the unseen power of sound to foresee storms and upheavals long before they struck. Zhang Heng, the same visionary behind the iconic seismoscope, was a master of marrying astronomy with earthly phenomena, while his dragon and frog earthquake detector stole the historical spotlight. His weather vane reveals a quieter genius. Picture a slender bronze pole topped with a delicately balanced wind-catching ornament like a bird or a banner. But this wasn't just for show, it was an acoustic oracle. The vane sat atop a hollow chamber filled with carefully tuned metal plates or strings. When distant storms approached, low-frequency infrasound waves inaudible to human ears would resonate through the chamber, causing the vane to tremble or pivot subtly. This movement hinted at coming turbulence, giving farmers and sailors days of advance warning. How did it work? Modern acoustics suggest Zhang Heng exploited a principle called sympathetic resonance. Just as a tuning fork vibrates when another of the same pitch is struck nearby, the weather vane's internal components were calibrated to respond to specific frequencies linked to atmospheric disturbances. Historical texts describe the device singing before the wind, a poetic nod to its predictive power. Unlike crude wind vanes that merely showed current gusts, Zhang Heng's design listened to the sky's hidden whispers. The weather vane's precision was no accident. Zhang Heng likely drew inspiration from ancient musical scale systems where pitch and harmony were tied to natural order. By aligning his device's resonant frequencies with those produced by brewing storms, like the deep rumbles of distant thunder or pressure waves from colliding fronts, he created an early form of atmospheric surveillance. Some scholars argue it could even detect seismic precursors, the same subterranean murmurs that his seismoscope later mapped. What's astonishing is how this technology parallels modern meteorology. Today, infrasound monitors track storms and volcanic eruptions by capturing ultra-low frequency waves, just as Zhang Heng's vane did 2,000 years ago. In 2017, researchers at Nanjing University recreated a replica using period-accurate materials and found it responded reliably to storm-generated infrasound within a range of several miles. The team noted its sensitivity rivaled early 20th century barometers, proof that ancient innovation often outpaced the tools of later eras. Beyond its utility, the weather vane reflects a profound philosophy that nature speaks in frequencies, not just forces. For Zhang Heng, forecasting wasn't about control but harmony, a theme echoing the Inca stonework. While the Andes architects danced with earthquakes, China's polymath composed duets with the wind. Both remind us that the greatest ancient technologies weren't just tools but dialogues with the natural world. As we marvel at this fusion of art and acoustics, let's prepare to unravel another mystery, one etched not in bronze but in fire and shadow. The Byzantine Empire's most feared weapon, Greek fire, awaits its turn in the spotlight. Now, let's step from the realm of sound and storms into the surprisingly advanced world of ancient medicine, where Roman surgeons wielded tools so precise they wouldn't look out of place in an operating room today. Buried under the ash of Mount Vesuvius in Pompeii, archaeologists uncovered a treasure trove of surgical instruments, scalpels, forceps, and even bone drills that reveal a level of medical sophistication centuries ahead of its time. The most striking finds were the scalpels, crafted from bronze or iron with detachable steel blades. These instruments mirrored the exact proportions of modern surgical knives. Some even had ergonomic handles designed to fit snugly in a surgeon's palm, reducing fatigue during lengthy procedures. The blades came in multiple shapes: sharp, pointed for incisions, curved for excisions, and serrated for sawing tissue, showcasing a nuanced understanding of surgical need. One particularly well-preserved scalpel from Pompeii's House of the Surgeon still had traces of its original hinge, allowing the blade to fold into the handle like a pocket knife, a feature still prized in today's medical tools. Then there were the forceps. Romans used at least 7 distinct types, each tailored for specific tasks. Spring forceps, with their scissor-like action, could clamp blood vessels or extract arrowheads. Toothed forceps gripped slippery tissues during eye surgeries, while bone forceps with wide, flat jaws stabilized fractures. The most ingenious were the polypus forceps, curved, spoon-ended tools used to remove nasal polyps. Their design was so effective that 19th-century surgeons replicated them almost unchanged after rediscovering Pompeii's artifacts. But the real showstopper: the trephination drills. These hand-cranked devices, resembling modern orthopedic drills, had rotating bits to bore into skulls for relieving brain pressure or treating fractures. Remarkably, they included a central pin to prevent the drill from penetrating too deeply, an ancient safety feature. Skeletal remains from Pompeii show clean, healed trephination holes, proving these procedures weren't just experimental but routinely successful. Some drills even had interchangeable bits for different bone densities, a level of specialization unheard of until the Industrial Revolution. How did Roman surgeons achieve such precision? Part of the answer lies in their metallurgy. They pioneered a technique called stainless bronze, alloying copper with tin and arsenic to resist corrosion, critical for preventing infections. They also understood sterilization, boiling tools in vinegar or heating them in flames before use, concepts that wouldn't be formalized until the 19th century. Medical texts from the era, like Cornelius Celsus's De Medicina, detail procedures for hernias, cataracts, and even plastic surgery, all performed with these very instruments. The Pompeii collection also hints at a surprising lack of primitive tools. Unlike earlier civilizations that relied on flint or obsidian, Roman surgeons had fully transitioned to reusable metal implements, some with ornate ivory handles denoting a surgeon's elite status. This wasn't battlefield triage gear but a refined profession with standardized equipment. Archaeologists found identical tools across the empire from Britain to Syria, suggesting formalized training and trade networks. Modern surgeons testing replicas of these tools report unexpected efficiency. A 2018 study in the Journal of Archaeological Science found Roman bone drills required 30% less force than early medieval versions, thanks to their balanced weight distribution. Even their needle holders, with their cross-hatched gripping surfaces, outperformed 16th-century designs in suture precision. What makes these tools truly revolutionary is their enduring legacy. When Renaissance physicians like Ambroise Paré sought to advance surgery, they didn't invent new instruments. They dug up Roman blueprints. From the scalpel's double-edged versatility to the forceps Chinese letter-like grip, these designs became the bedrock of Western medicine. Walking through a Pompeii exhibit today is like touring a mirror of the surgical tray beside you. Proof that brilliance isn't always about invention, but often about perfecting what already works. As we close this chapter on Rome's medical mastery, let's turn our attention to a technology that transformed not health but entertainment. Heron of Alexandria's automatic theater, where steam-powered puppets staged dramas without human hands. Leaving behind the precision of Roman scalpels, let's venture into a world where steam and strings brought myths to life. Heron of Alexandria's automatic theater. Picture this, an hour-long play performed entirely by self-moving puppets, powered by nothing more than ropes, counterweights, and hissing steam. This wasn't just entertainment, it was the first known instance of programmable robotics, predating modern animatronics by nearly 2,000 years. At the heart of this marvel was Heron's genius for converting basic physics into spectacle. His miniature theater, roughly the size of a modern coffee table, used a rotating cylindrical drum studded with pegs, much like a music box's mechanism. As the drum turned, the pegs tugged on ropes connected to wooden puppets, making them gesture, walk, or even fight in sync with a musical accompaniment. But the real showstopper was the steam power. Heron rigged a hidden boiler to release timed bursts of steam, causing doors to swing open, miniature ships to sail across a stage ocean, and even thunderous sound effects to erupt during dramatic moments. Archaeologists believe one play depicted the myth of Nauplius, where automated flames simulated the burning of Greek ships, a feat that would stun audiences today. What made this theater revolutionary wasn't just its mechanics but its programmability. By rearranging the pegs on the drum, Heron could alter the entire sequence of movements, essentially coding different performances. This concept mirrors modern robotics, where changing a script alters a machine's actions. The precision was astonishing. Some puppets had up to 7 points of articulation, allowing them to kneel, raise arms, or turn their heads, movements later replicated in 18th century automata. Heron didn't stop at theater. His inventions blurred the line between ritual and engineering. Take his automatic temple doors. When priests lit a fire on the altar, heated air expanded into hidden pipes, pumping water into counterweighted buckets. Once heavy enough, the buckets pulled ropes that swung the temple doors open by divine will, dazzling worshippers. Similarly, his coin-operated holy water dispenser, a bronze vessel where dropping a drachma triggered a measured pour, anticipates modern vending machines by millennia. Modern engineers rebuilding Heron's devices face unexpected challenges. A 2016 MIT study found his steam valves required near-perfect calibration. Even a slight misalignment would jam the mechanisms. Yet when reconstructed accurately, the theater ran flawlessly for its full 60-minute duration, with automated scene changes and puppet dialogues. This reliability suggests Heron's workshops likely employed standardized parts, an early form of mass production. The legacy of these inventions stretches further than you might think. Renaissance inventors like Leonardo da Vinci studied Heron's pneumatic designs, while his weight-driven pulley systems inspired medieval clock towers. Even Disney's Imagineers acknowledge his theater as a conceptual forerunner to attractions like the Hall of Presidents. But perhaps the most poignant detail. Heron's surviving writings describe his automata as thaumaata miracles. In an age where technology often feels sterile, his creations remind us that engineering can still spark wonder. Next, we'll examine how ancient defenses could hold their own against modern weaponry, starting with the Carthaginians' ingenious harbor shield. Now, let's shift our focus from the wonders of automation to the fierce world of ancient naval warfare, where the Carthaginians engineered a near-impenetrable shield for their harbors. Imagine a bustling Mediterranean port, the lifeblood of Carthage's trading empire, guarded not just by soldiers but by a floating fortress of wood and iron, the legendary harbor boom. This wasn't just a barrier, it was a masterclass in maritime defense, designed to outsmart even the most determined invaders. At its core, the Carthaginian boom was a deceptively simple yet devastatingly effective concept. Picture a massive chain forged from interlinked iron segments, stretched taut across the harbor's entrance. Beneath it, wooden beams, some as thick as tree trunks, floated horizontally, creating a wall-like barrier that could withstand the brute force of enemy ships. Historical accounts suggest the chain alone weighed several tons, requiring a system of pulleys and winches operated from fortified towers on either side of the harbor. When danger loomed, Carthaginian defenders could raise or lower the boom in minutes, transforming their port into an aquatic stronghold. But the real genius lay in its adaptability. Unlike static defenses, the boom was modular. During peacetime, sections could be detached to allow friendly ships to pass, then swiftly reassembled when threats emerged. This flexibility mirrored modern naval tactics, where harbors today use retractable barriers or submarine nets for controlled access. Archaeologists studying the ruins of Carthage ports have found evidence of rotating mechanisms embedded in stone quays, hinting at a system that could adjust the boom's tension or angle to counteract tides or battering rams. The boom's most famous test came during the Punic Wars, when Rome's navy repeatedly tried and failed. To break through, one Roman admiral, according to ancient texts, ordered his ships to ram the barrier at full speed, only to watch their hulls splinter against the reinforced wood while the chain held firm. Frustrated, the Romans resorted to nighttime raids, but Carthaginian sentries stationed on the harbor towers used fire signals to alert the city, proving the system was as much about intelligence as brute strength. Modern engineers have noted surprising parallels between this ancient tech and contemporary defenses. The principle of a floating barrier reappears in everything from anti-submarine nets used in World War II to the booms deployed today to contain oil spills or deter pirates. What's striking is how the Carthaginians anticipated the need for layered defense. Their harbors often combine the boom with underwater obstacles like submerged stakes, creating a gauntlet that forced enemies into kill zones where archers and catapults could pick them off. Yet the boom's legacy isn't just about warfare. Its design influenced later harbor engineering, from Byzantine chain barriers to medieval portcullises. Even the Vikings, masters of naval raids, adopted similar concepts, using log booms to protect their fjords. But perhaps the most enduring lesson is in resourcefulness. The Carthaginians built their boom not with exotic materials but with locally sourced iron and timber, proving that ingenuity often trumps extravagance. As we marvel at this ancient feat of engineering, we're reminded that the past holds blueprints for problems we still face today: how to defend, adapt, and innovate with what's at hand. Next, we'll journey to Mesoamerica, where the Olmecs turned nature's gifts into something truly revolutionary: the world's first vulcanized rubber. Leaving behind the clash of naval warfare, let's step into the vibrant world of the Olmecs, where a seemingly simple material, rubber, became the foundation of a technological breakthrough far ahead of its time. Picture the humid lowlands of ancient Mesoamerica, where towering pyramids cast shadows over bustling marketplaces, and the air thrums with the sound of a game unlike any other. Here, players wielded not just skill but a revolutionary invention: the world's first vulcanized rubber balls, crafted millennia before Charles Goodyear patented his process. The Olmecs, often called the mother culture of Mesoamerica, didn't just stumble upon rubber, they mastered it. Their secret lay in the sap of the native rubber tree, Castilla elastica, which they harvested and transformed through a process that still astonishes chemists today. By mixing the raw latex with juice from the morning glory vine, they triggered a molecular reaction that stabilized the rubber, making it elastic, durable, and resistant to decay. Modern experiments replicating this technique confirm it's a rudimentary form of vulcanization, predating Goodyear's sulfur-based method by roughly 3,000 years. These rubber balls weren't mere toys. They were central to the Olmecs' most sacred ritual, the Mesoamerican ball game. Played in massive stone courts flanked by sloping walls, the game was a high-stakes blend of sport, politics, and spirituality. Players used their hips, elbows, or even stone bats to propel the heavy ball weighing up to 9 pounds across the court, aiming to pass it through stone rings mounted high on the walls. The rubber's bounce added a dynamic, unpredictable element, turning each match into a spectacle of athleticism and strategy. But the stakes were life and death. Some historians believe the losing team's captain, or even the entire team, might be sacrificed to the gods, their blood ensuring cosmic balance. What's equally fascinating is how the Olmecs scaled their rubber production. Archaeological sites like El Manotti, a sacred sacrificial bog, have yielded dozens of rubber balls preserved in the oxygen-poor water, offering a rare glimpse into their craftsmanship. The balls vary in size and density, suggesting tailored designs for different games or rituals. Some even contain human fingerprints pressed into the surface, ghostly reminders of the artisans who shaped them. The Olmecs' rubber technology didn't stop at balls. Evidence hints at its use in waterproofing textiles, creating adhesive bindings for tools, and even fashioning rubber-soled sandals for elite travelers. This versatility mirrors modern applications, from car tires to surgical gloves. Yet, unlike today's industrial processes, the Olmecs achieved this with nothing more than natural ingredients and empirical knowledge passed down through generations. By the time the Aztecs and Maya inherited the ball game, rubber had become a luxury commodity traded across empires like precious gemstones. The Aztecs called it ole, a word that lives on in Olmec and Mexico's Huel rubber. Spanish conquistadors, encountering the bouncing balls for the first time, marveled at their properties, with one chronicler comparing them to enchanted apples that defied gravity. Today, the Olmec's legacy vibrates in every rubber product we use. Their innovation challenges the myth that vulcanization was a 19th century revelation, proving instead that ancient scientists had cracked the code through observation and experimentation. As we trace the arc from ritual courts to modern factories, the lesson is clear. Sometimes the most advanced technologies aren't new at all. They're rediscoveries of what our ancestors already knew. Next, we'll turn our gaze skyward, where the Egyptians mapped the heavens with astonishing precision, transforming tomb ceilings into celestial timekeepers. Now, let's journey from the bouncing rubber courts of the Olmecs to the silent, starlit chambers of ancient Egypt, where the heavens weren't just observed, they were transformed into a grand celestial clock. Imagine standing in the dim glow of an oil lamp, your eyes tracing the vaulted ceiling of a pharaoh's tomb, where every painted star and constellation served as a precise timekeeping device. This was the genius of Egyptian star clocks, an astronomical innovation so advanced it laid the groundwork for modern sky mapping software. The Egyptians didn't merely worship the stars, they harnessed them. Around 3,500 years ago, during the New Kingdom, they began decorating tomb ceilings with intricate star charts known as diagonal star clocks. These weren't static artworks but dynamic tools designed to track time through the night. Each clock consisted of 36 decans, groups of stars arranged in diagonal rows. As the night progressed, a specific decan would rise above the horizon, signaling the start of a new hour. Priests and astronomers used these charts to divide the night into 12 equal segments, creating one of history's earliest standardized timekeeping systems. What makes these clocks extraordinary is their adaptability. Unlike rigid sundials, star clocks worked year-round, accounting for Earth's shifting position relative to the stars. The Egyptians even adjusted their charts over centuries as precession, the slow wobble of Earth's axis, gradually altered the night sky. Archaeologists have found multiple versions of these clocks in tombs like those of Senon, Mut, and Seti I, each updated to reflect celestial changes. This meticulous record-keeping reveals an understanding of astronomy far ahead of its time. The star clocks weren't just practical, they were deeply spiritual. Egyptians believed the decans were divine beings guiding the pharaoh's soul through the afterlife. The rising of Sirius, the brightest star, marked the annual Nile flood, linking timekeeping to agriculture and mythology. This fusion of science and religion echoes modern GPS systems, which rely on satellite constellations named after ancient gods. Modern researchers have tested these clocks using planetarium software, confirming their accuracy to within 15 minutes. Some decans, like those in the constellation Orion, still align with their ancient positions today. This precision suggests the Egyptians may have used viewing tubes or sighting tools to enhance observations, much like early telescopes. Beyond tombs, star clocks influenced Egyptian architecture. Temples like Karnak were aligned to solstice sunrises, while the Great Pyramid's air shafts point directly to key stars, possibly serving as giant astronomical instruments. This holistic approach, blending art, science, and spirituality, foreshadowed today's integrated tech, where apps like Stellarium turn smartphones into portable planetariums. The legacy of Egyptian star clocks endures in unexpected ways. Their decanal system evolved into the 24-hour day we use now, and their star maps share striking similarities with modern astronomical charts. When you check a weather app for moon phases or use a telescope mount calibrated to celestial coordinates, you're tapping into knowledge first systematized by ancient Egyptian sky watchers. As we marvel at their achievements, a profound truth emerges. The desire to decode the cosmos isn't a modern obsession but a timeless human pursuit. Next, we'll witness how another civilization turned warfare into an engineering art form with the Hittites' revolutionary chariots, where speed and agility redefined ancient combat. Shifting gears from the celestial mastery of Egypt, we encounter a machine that transformed the battlefield, the Hittite chariot. Picture this, a fleet of these agile war machines thundering across the plains, their spoked wheels kicking up dust as archers launch volleys with pinpoint accuracy. This wasn't just a vehicle, it was the tank of the Bronze Age, a game-changer that redefined military strategy. The Hittites, an empire centered in modern-day Turkey around 3,600 years ago, didn't invent the chariot, but they perfected it. Earlier models, like those used by Mesopotamia, were clunky four-wheeled carts pulled by donkeys. The Hittite version was a marvel of lightweight engineering. Their chariots weighed as little as 65 pounds, thanks to frames made of flexible ash wood and wheels with just 4 to 6 spokes, a radical reduction from the solid discs used by rivals. This design allowed speeds up to 25 miles per hour, faster than any infantry could retreat. What truly set these chariots apart were 3 innovations. First, the axle placement. By moving it to the rear of the platform, the Hittites created better weight distribution, preventing the chariot from tipping during sharp turns. Second, they used seasoned hardwood for wheels, which resisted warping even in humid climates. Archaeologists have found wheels with rawhide tires, an ancient version of shock absorption. Third, and most crucially, they bred a new type of horse. Hittite texts describe training regimens for the fleet ones from the east, likely ancestors of the Arabian horse, capable of pulling these lightweight chariots for hours. The impact on warfare was staggering. A single Hittite chariot crew, typically a driver and an archer, could dominate a battlefield. At the famous Battle of Kadesh in 1274 BCE, the Hittite king Muwatalli II deployed nearly 3,500 chariots against the Egyptians. Contemporary carvings show Hittite archers firing from moving platforms while Egyptian soldiers scrambled for cover. This was combined arms warfare centuries before the term existed. Modern experiments reveal why these chariots were so lethal. Replicas based on tomb paintings and surviving metal fittings demonstrate that a Hittite archer could loose 15 arrows per minute while moving comparable to the rate of fire from a medieval longbow. The chariot's maneuverability let them execute the swarm tactic, encircling enemy formations like a pack of wolves. Resistance was feudal infantry armed with bronze swords couldn't outrun them, and early armor couldn't stop their arrows. But the brilliance extended beyond combat. The Hittites maintained elaborate chariot factories with standardized parts that could be swapped in the field, an early example of modular design. Clay tablets from their capital, Hattusa, list quality control measures for axles and wheels, proving they understood mass production. Some chariots even featured bronze-scale armor for horses, showing an unprecedented concern for animal survivability. The decline of Hittite chariots came not from obsolescence but from climate change. Around 1200 BCE, a megadrought collapsed empires across the Mediterranean. Without grasslands to feed their horses, the Hittite war machine disintegrated. Yet their legacy endured. The Assyrians later adopted their designs, and traces of spoked wheels appear in Celtic and Roman vehicles. Today, you can see echoes of Hittite engineering in modern armored vehicles. The principle of combining speed, precision firepower, and crew coordination defines everything from main battle tanks to drone swarms. Even racing cars owe a debt to those Bronze Age wheelwrights. The optimal weight-to-power ratio they pioneered remains central to vehicle design. As we leave the dust of ancient battlefields behind, prepare to encounter an object that proves the ancients could not only shape metal but bend light itself. The Nimrod lens, a 3,000-year-old piece of crystal that may have been the world's first telescope. Now let's turn our gaze to an ancient art form that transformed sand into treasures: Mesopotamian glassmaking. While the Hittites were revolutionizing warfare with chariots, civilizations between the Tigris and Euphrates rivers were mastering a craft so sophisticated it would take modern science centuries to decode their secrets. The Mesopotamians didn't just make glass, they engineered it. Around 3,500 years ago, artisans in cities like Ur and Nineveh were producing vibrant colored glass with precision that rivals today's laboratories. Their recipe tablets, pressed into clay in cuneiform script, reveal startling complexity. They mixed sand with plant ash for alkali, added lead or antimony for clarity, and used metals like cobalt and copper to create dazzling blues and reds. But here's what stuns archaeologists: their color formulas weren't accidental. A British museum study showed Mesopotamian blue glass contained exactly 7% cobalt oxide, identical to modern pigment standards. Their crowning achievement, lens making, the Nimrud lens found in modern Iraq and dating to 700 BCE, proves they weren't just decorating palaces, they were bending light. This oval-shaped rock crystal, about the size of a palm, magnifies objects when held at arm's length. While some argue it was a decorative inlay, its precisely ground curvature suggests intentional optical use. Assyrian texts describe seeing stones that helped scribes with tiny cuneiform characters, and recent experiments show the Nimrud lens can focus sunlight to start fires, ancient science at work. What made Mesopotamian glass exceptional was their control over chemistry. They developed the first glass factories, with furnaces reaching 2,000 degrees Fahrenheit, hot enough to melt quartz. Workers used long blowpipes centuries before Roman glassblowing emerged, shaping molten glass around clay cores to create vessels. But their real innovation was color consistency. By adding manganese, they created transparent glass, a breakthrough Europeans wouldn't replicate until the Middle Ages. Their red glass, infused with nanoparticles of gold and copper, still dazzles in museum cases today. The process was remarkably systematic. Cuneiform tablets from the library of Assyrian King Ashurbanipal detail multi-step procedures, like this one for lapis lazuli-colored glass. Take 60 parts sand, 30 parts alkali from seaweed, 5 parts copper, and heat for 2 days until it flows like honey. Modern chemists reconstructed these recipes and were stunned. The Mesopotamians had essentially invented the scientific method, recording failures and successes with meticulous detail. Beyond beauty, their glass had practical uses. Archaeologists have found concave glass pieces in Babylonian ruins that may have served as burning glasses for medicine, focusing sunlight to cauterize wounds. Others appear to be early magnifiers for intricate jewelry work. A tablet from Sippar describes a healing disc of blue glass placed on wounds, possibly recognizing glass's antibacterial properties when combined with copper salts. The legacy of Mesopotamian glassmakers echoes through history. Their cobalt blue recipe became the prized ultramarine of Renaissance painters. Their lens grinding techniques may have inspired later Greek and Roman opticians. Even today, the Corning Museum of Glass displays reconstructed Mesopotamian pieces beside smartphone Gorilla Glass, noting how ancient alkali formulas influence modern durability coatings. As we marvel at these translucent wonders, remember, every time you pick up a drinking glass or adjust your glasses, you're touching a technology refined by Mesopotamian innovators who saw potential where others just saw sand. Next, we'll uncover how another civilization turned wind into air-conditioning Persian wind catchers that cooled entire cities without a single watt of electricity. Now, let's journey from the gleaming glass of Mesopotamia to the ingenious water-moving marvels of ancient China. While the Mesopotamians were perfecting their translucent chemistry, Chinese engineers of the Han Dynasty were solving one of agriculture's greatest challenges: how to lift water efficiently to higher fields. Their solution, the chain pump, a deceptively simple yet revolutionary device that became the mechanical great-grandparent of everything from bicycle chains to factory conveyor belts. Picture this, a continuous loop of wooden plates connected by hinged joints, exactly like the chain on your bicycle, but instead of turning gears, it's lifting water. The chain pump's design was brilliantly straightforward. Workers would turn a large horizontal wheel by foot pedals or animal power, which rotated a vertical loop of square wooden pallets through a trough. As each pallet dipped into the water source, it scooped up liquid, carrying it upward until tipping over at the top, delivering water to irrigation channels. Some massive versions could lift water over 30 feet, transforming previously uncultivable hillsides into terraced rice fields. What made this second-century invention extraordinary was its efficiency. Unlike the shadoof, a counterweighted bucket system used in Egypt, or the Archimedes screw, the chain pump moved water continuously without spillage. Farmers could operate it for hours with minimal effort, and its modular design allowed scaling, adding more sections to reach greater heights. The earliest known depiction appears in a Han Dynasty tomb mural from around 125 CE, showing two laborers casually operating one while chatting, proof of its labor-saving design. But the real stroke of genius was in the mechanics. Those interlocking wooden plates were essentially the first endless chain transmission, a concept that wouldn't reappear in Europe until the sketches of Leonardo da Vinci over 1,300 years later. Modern engineers analyzing Han-era chain pumps found they used the same principles as today's industrial bucket conveyors. The angled pallets created watertight compartments when submerged, then opened slightly to release water at the top. Some excavated examples even show bronze bushings reducing friction at pivot points, an early form of mechanical bearing. The chain pump's impact was immense. It enabled the expansion of wet rice cultivation across China's varied terrain, directly supporting population growth. During the Three Kingdoms period, records describe armies using portable versions for siege warfare, filling moats by night to surprise enemies. Variants spread along trade routes, influencing Korean Nabat pumps and Persian Sakia wheels. Even today, you can find farmers in rural Anhui province using nearly identical designs passed down through generations. Perhaps most surprisingly, this ancient invention holds lessons for modern engineering. Researchers at Tsinghua University recently built a Han-style chain pump and found it 30% more energy efficient than modern electric pumps for low-height water transfer. The secret, its slow, steady motion avoids turbulence and backflow. Meanwhile, the chain and sprocket principle it pioneered now drives everything from bicycle drivetrains to motorcycle engines to assembly lines, all descendants of an irrigation tool dreamed up 2 millennia ago. So the next time you ride a bike, glance at that chain linking pedal to wheel. You're looking at the direct heir of a Han Dynasty breakthrough that turned human ingenuity into flowing water, then into one of humanity's most enduring mechanical concepts. Speaking of enduring ideas, our next stop takes us to the battlefields of Rome, where engineers created torsion-powered artillery so precise they could snipe enemy commanders at 300 paces. Welcome to the terrifying world of Roman ballistae. Now, let's shift from the agricultural ingenuity of ancient China to the military brilliance of Rome, where engineers turned physics into fear on the battlefield. The Roman ballistae were not just weapons, they were masterpieces of precision engineering, combining raw power with sniper-like accuracy. Imagine a machine so exact it could pick off enemy officers from the length of 3 football fields, changing the course of battles before they even began. At the heart of the ballista's deadly efficiency was its torsion mechanism. Unlike earlier catapults relying on tension or counterweights, Roman engineers harnessed the power of twisted ropes. Here's how it worked. 2 vertical wooden frames each held a bundle of sinew or horsehair ropes, twisted to unbelievable tension with a winch. When released, these bundles unwound with explosive force, launching projectiles at speeds approaching 170 miles per hour. The genius lay in the symmetry. Both arms moved in perfect unison, eliminating vibration and ensuring straight, stable flight. The ammunition options showed terrifying versatility. For tearing through fortifications, they hurled 10-pound stone balls carved from volcanic basalt. Against troop formations, deadly 6-foot bolts with iron tips could impale 3 soldiers in a row. Naval versions fired grappling hooks to reel in enemy ships like fish. But the real innovation was in the adjustable mechanisms. A crew could modify torsion, tightness, and trajectory in seconds, allowing the same ballista to switch from arcing shots over walls to flat trajectories across open fields, ancient multitasking at its deadliest. Accuracy was where these machines truly shined. Historical accounts describe ballistae hitting specific targets at over 400 yards, a distance where most archers would struggle to see their enemy. During Julius Caesar's siege of Avaricum, his engineers reportedly shot down individual defenders from the ramparts one by one, creating psychological terror. Modern reconstructions confirm this precision. At 50 yards, a skilled crew could reliably hit a man-sized target, and at 100 yards they could strike a formation with devastating effect. Maintaining this edge required Roman equivalent of special forces training. A well-drilled crew of 4 could launch up to 4 bolts per minute, each member performing timed steps like a machine. The gunner used a calibrated rear sight and elevation wheel, adjusting for wind like a modern artillery officer. Surviving maintenance manuals detailed daily checks measuring rope moisture to maintain consistent torsion, replacing frayed strands before they snapped, and lubricating metal parts with animal fat to prevent squeaks that might reveal positions at night. The logistical impact was revolutionary. Modular designs allowed disassembly into mule portable packs, letting Rome's armies deploy artillery anywhere. During the Dacian Wars, Trajan's forces reportedly maneuvered ballistae through mountain passes to bombard hill forts thought impregnable. Some fortress versions had swiveling bases allowing 300-degree firing arcs, an innovation borrowed from naval designs. The psychological effect multiplied their power. Tribes who'd never seen such weapons often surrendered at the sound of the first volley's distinctive twang thud. What's truly humbling is how these machines blurred the line between ancient and modern. The ballista's adjustable sights and calibrated elevations wouldn't look out of place on a 20th century howitzer. When archaeologists examined bolts from Masada, they found standardized iron tips with weight tolerances tighter than some modern ammunition. Even the Romans knew they'd created something extraordinary. Reliefs on Trajan's columns show ballistae crews treated as elite units, their weapons often decorated like prized race cars. Perhaps the ultimate testament to their design came 2,000 years later. During World War I, British officers studying Roman siege techniques realized something startling. The ballista's effective range matched no man's land distances on the Western Front. In 1917, engineers actually built a torsion-powered ballista to lob grenades silently across trenches when gunfire would reveal positions. The machine worked flawlessly, proving Roman physics still held merit in the age of artillery. As we leave these ancient snipers of the battlefield, consider how their legacy lives on. From the adjustable sights on modern rifles to the twist mechanisms in today's sporting crossbows, the ballista's DNA endures. Next time you watch a war movie featuring pinpoint artillery strikes, remember the Romans were doing it with twisted ropes and wooden frames when Europe's ancestors were still living in huts. And speaking of huts, our next stop takes us to the windy deserts of Persia, where engineers turned whole buildings into natural air conditioners using nothing but clever architecture prepared to be cooled by the ingenuity of wind catchers. From the thunderous battlefields of Rome, we now step into the echoing halls of ancient Greece, where engineers traded catapults for chords and warfare for water-powered music. Hidden in this shift from destruction to artistry lies one of history's most overlooked marvels. The hydraulis, the world's first pipe organ, where physics and melody danced in perfect harmony. Picture a device so ingenious it used water to tame air, creating musical precision unrivaled for centuries. Invented in the 3rd century before the Common Era by the brilliant engineer Ctesibius of Alexandria, the hydraulis wasn't just an instrument, it was a revolution in sound. At its core lay a deceptively simple principle: water pressure stabilizing airflow to pipes, eliminating the wavering notes plaguing earlier wind instruments. Here's how this aquatic maestro worked. A hand pump forced air into a chamber submerged in water, creating a pressurized reservoir. As the musician pressed keys, valves released this air into individual bronze pipes, each tuned to a specific pitch. The water's constant weight acted like a natural regulator, ensuring steady pressure no matter how vigorously the pump was worked. This meant notes held their tone perfectly, a feat impossible with breath-powered instruments like flutes or trumpets. The hydraulis could whisper delicate melodies or thunder with the power of 50 musicians, all controlled by one player's fingertips. The craftsmanship was staggering. Surviving diagrams show pipes ranging from reed-thin to as wide as a man's arm, arranged in ranks like soldiers. Some organs had multiple pump operators working in shifts during performances, their synchronized efforts maintaining unbroken pressure for hours. The largest hydraulis, described in accounts from Antioch, needed 12 slaves working its bellows and stood 2 stories tall, its deepest pipes producing tones that vibrated spectators' ribcage. But why water? The Greeks realized liquid's incompressibility made it ideal for smoothing airflow. Unlike modern organs relying on weighted bellows, the hydraulis's water chamber absorbed sudden pressure changes, preventing the gasping effect heard in early bagpipes. Archaeologists found evidence that some models even used adjustable water levels to shift octaves mid-performance. A 3rd century pitch control. The hydraulis wasn't confined to temples. It became the soundtrack of Roman spectacle, accompanying gladiator combats in the Colosseum where its deep drones heightened tension. Nero famously played one during the Great Fire of Rome, leading to rumors he fiddled while the city burned, a mistranslation as the hydraulis was his instrument of choice. Even in decay, its influence endured. Byzantine emperors sent hydraulis experts as diplomatic gifts to Charlemagne's court, where their knowledge seeded Europe's medieval organ tradition. Modern reconstructions reveal shocking sophistication. In 2014, researchers built a working hydraulis using ancient descriptions. The result produced tones eerily similar to modern church organs, with a distinctive, liquid resonance experts compare to hearing music underwater. The team discovered subtle design choices, like angled pipes and tapered windways that reduced turbulence, showing an understanding of fluid dynamics centuries before the science existed. What makes the hydraulis truly timeless is how its innovations echo today. The principle of regulated air pressure lives on in everything from woodwind instruments to ventilator machines. Its keyboard layout became the blueprint for pianos and synthesizers. Even the word hydraulic traces back to this marriage of water and art. As the last notes of this aquatic symphony fade, we turn our gaze eastward to where another ancient marvel harnessed nature's forces not for music or war, but for comfort. In the scorching Persian deserts, engineers sculpted the wind itself into a cooling embrace through towers that functioned like nature's air conditioners. The ingenuity of wind catchers awaits. Beneath the blazing sun of ancient India, where monsoons could bring both life and ruin, engineers sculpted stone into a breathtaking solution: stepwells, monuments of survival as elegant as they were ingenious. These weren't just water sources, but subterranean cathedrals where every step married form and function, descending deep into the earth to kiss the water table. Imagine a structure where architecture defied gravity, not by rising upward but by carving downward. Stepwells like Gujarat's Rani Kai Vav or Rajasthan's Chand Bayori weren't mere wells with staircases, they were inverted palaces. Their symmetrical steps formed geometric masterpieces, some descending over 10 stories deep, with thousands of steps fanning out like a stone tapestry. But this beauty served a brutal purpose, surviving drought. In regions where surface water vanished for months, stepwells tapped into groundwater, their tiered design allowing access even as levels dropped. The engineering brilliance lay in their adaptability. Unlike modern wells with fixed pumps, stepwells functioned like adjustable water gauges. During monsoons, villagers used higher steps. As droughts progressed, they descended further, always maintaining contact with the receding water. Some wells featured intricate filtration systems. Sand and charcoal layers purified water before it reached the main reservoir. Others had sluice gates to control flow, preventing collapse during flash floods. But stepwells were more than utilities, they were community hubs. Carved niches housed shrines, turning water collection into ritual. Shadowed alcoves offered cool respite from the heat, sometimes reaching temperatures 20 degrees lower than the surface. Traders paused here, pilgrims rested, and elders taught geometry by tracing the steps' perfect angles. The Adalaj stepwell even includes whispering galleries, where voices carry eerily across corners, proving acoustics were part of the design. Modern hydrologists still puzzle over their precision. Without telescopes or levels, builders aligned stepwells to celestial markers. The Surya Kund steps form 108 triangles, a sacred number in Hinduism, while also acting as a solar calendar. Shadows touch specific carvings only on equinoxes. Even more astounding is their self-repairing nature. Many stepwells use a lime and jaggery mortar that grows stronger when wet, sealing cracks during rains. Today, these structures inspire sustainable design. Architects study their passive cooling. Air sinks down the steps, creating natural ventilation. Urban planners replicate their water management principles in cities like Chennai, where ancient stepwell logic now guides rainwater harvesting. And in a poetic twist, Rajasthan's Neemrana stepwell has been repurposed as a performance space. Its acoustics perfect for music, proving that even after 1,000 years, these wells still quench more than just thirst. As the echoes of these stone symphonies linger, we journey to where another civilization turned necessity into artistry. Far across the oceans, the Aztecs didn't just farm land. They created it, crafting floating gardens that fed an empire. The miracle of Chinampas awaits. Now, let's wade into the shallow waters of ancient Mesoamerica, where the Aztecs faced a challenge as daunting as India's droughts, but their solution didn't dig downward. It floated. In the heart of Lake Texcoco, where swampy land seemed useless for farming, they engineered chinampas, floating gardens so productive they could harvest up to 7 crops a year, turning a lake into a breadbasket. Picture a grid of rectangular plots, each about 30 meters long, anchored to the lakebed but appearing to drift like lush islands. These weren't rafts but artificial islands built by weaving reeds and stakes into frames, then piling them with layers of sediment, decaying vegetation, and mud from the lake bottom, a compost-rich soil that stayed fertile for centuries. The Aztecs didn't just grow crops here, they designed an ecosystem. Willow trees planted along the edges stabilized the plots with their roots, while canals between the chinampas acted as waterways for canoes and natural irrigation channels. The genius lay in the water itself. Unlike conventional farms, chinampas leveraged capillary action, the same principle that helps plants draw water upward through their roots. The porous lakebed constantly replenished moisture, eliminating the need for manual watering. Meanwhile, the canals regulated temperature, protecting plants from frost and creating a microclimate that extended growing seasons. Modern tests revealed chinampa soil retains twice the nitrogen of ordinary farmland, thanks to the Aztecs' layering technique mimicking natural wetland cycles. But chinampas were more than high-yield farms, they were a template for sustainability. fish in the canals provided protein and nutrients for the soil through their waste. Ducks and frogs controlled pests naturally, avoiding the need for pesticides. Even the weeds had purpose. Water hyacinths were harvested to weave baskets or returned to the soil as green manure. This closed-loop system produced enough surplus to feed the sprawling city of Tenochtitlan, a metropolis larger than any European capital of its time. Archaeologists note the precision of their layout. Chinampas were spaced exactly 1 canoe width apart, ensuring efficient transport of goods. Each plot's orientation maximized sunlight exposure, while the alternating land and water pattern reduced erosion. The Aztecs even engineered seasonal floodgates, using woven barriers to control water flow during rains, an ancient version of flood management still studied by modern agronomists. Today, chinampas inspire urban farming revolutions. In Mexico City, where concrete has swallowed most of Lake Texcoco, activists are reviving these techniques to combat food deserts. Scientists praise their carbon footprint. Chinampa farming emits just 1/10 the greenhouse gases of industrial agriculture. Even NASA has taken note, researching their potential for sustainable food systems in space habitats. As the legacy of these floating gardens ripples through time, we're reminded that innovation isn't always about towering megastructures. Sometimes it's about working with nature, not against it. And speaking of nature's partnerships, our next marvel takes us to the frozen north, where Vikings turned a simple crystal into a maritime GPS, the legendary Sunstone. Now, let's sail north to the icy fjords of Scandinavia, where Viking warriors wielded a weapon so advanced it seemed forged by the gods themselves, the legendary Ulfberht swords. These weren't just tools of battle, they were masterpieces of metallurgy, centuries ahead of their time. Imagine a blade so sharp and flexible it could slice through chainmail like parchment, yet strong enough not to shatter on impact. What made these swords extraordinary wasn't just their deadly efficiency, it was the mystery of their creation. The secret lay in the steel. While most European swords of the Viking Age were made from bloomery iron, a crude, impure metal riddled with slag and weak spots, Ulfberhts were crafted from crucible steel, a material so pure it contained almost no imperfections. This high-carbon steel, with a carbon content of around 1.2%, gave the blades a near-mythical combination of hardness and elasticity. To put that in perspective, medieval European smiths wouldn't achieve similar quality until the Industrial Revolution, nearly 800 years later. But here's the puzzle. Crucible steel required temperatures exceeding 1,200 degrees Celsius, a heat so intense it could melt ordinary furnaces. So how did Viking smiths, working in the 9th to 11th centuries, accomplish this? The answer might lie in trade routes stretching all the way to the Middle East. Chemical analyses reveal Ulfberht steel shares striking similarities with Damascus steel, sourced from Persia and India. Vikings likely acquired this premium material through trade networks, possibly exchanging furs, amber, or slaves for ingots of this exotic metal. The craftsmanship was equally groundbreaking. Each Ulfberht bears the inscription +VLF Bur +T, a signature that served as both a brand and a mark of prestige. Scholars debate whether this referred to a single master smith, a guild, or even a royal armory. What's clear is that these swords were rare. Only around 170 have been found across Europe, suggesting they were reserved for elite warriors or chieftains. Modern tests reveal their superiority. When replicas were tested against conventional Viking swords, Ulfberhts bent at a 45-degree angle without breaking, while others snapped at 30 degrees. Their edges held sharpness longer, and their weight distribution made them faster in combat. Some historians argue these blades contributed to the Vikings' fearsome reputation, allowing them to dominate battles from England to Byzantium. Yet the Ulfberht tradition vanished as suddenly as it appeared. By the 12th century, the inscription stopped, and Europe's sword quality regressed for centuries. Some theorize that trade routes collapsed, cutting off access to crucible steel. Others suggest the secret died with a handful of master smiths. Either way, these swords became relics of a lost golden age of metallurgy. Today, Ulfberts inspire both awe and debate. Blacksmiths still struggle to replicate their exact properties, and historians ponder how Vikings, often stereotyped as brutish raiders, pioneered such advanced technology. Perhaps their greatest legacy is the reminder that innovation can emerge from the most unexpected places, even the forge of a Viking workshop. And as we leave the smoky glow of the blacksmith's fire, our next journey takes us to the sun-baked deserts of Persia, where ancient engineers turned wind into air conditioning. Now let's step back even further in time to the banks of the Nile, where ancient Egyptians weren't just building pyramids, they were also revolutionizing home security. Long before deadbolts and keypads, they engineered the world's earliest known pin tumbler locks, a design so ingenious it's still the foundation of modern locks today. Picture this, a wooden bolt sliding into a doorframe, but with a clever twist. Embedded inside were vertical pins of varying lengths held in place by gravity. To open it, you'd insert a key, a flat piece of wood with pegs matching the exact pin arrangement. Lift the key, and the pins would align perfectly at the shear line, allowing the bolt to slide free. Get it wrong, and the pins would jam the mechanism, keeping intruders out. Sound familiar? It's the same basic principle used in today's cylinder locks, from your front door to high-security vaults. What's astounding is how refined these locks were for their time. Archaeologists have found examples dating back to 4,000 years ago in the ruins of Pharaoh Khafre's palace. Craftsmen carved them from durable sycamore wood, with pins so precisely measured that tolerances were within millimeters. Some even had multiple rows of pins, an early form of multi-point locking. And they weren't just for royalty. Evidence suggests wealthy merchants and temple officials used them to protect valuables like grain stores or sacred artifacts. But here's where Egyptian locks outsmarted later designs. Unlike Roman or medieval locks that relied solely on metal wards which thieves could pick by feel, the pin tumbler system required exact key precision. Without seeing the internal pins, a robber would need trial and error to guess the pin heights, a near impossible task without modern tools. This made Egyptian locks remarkably resistant to tampering for their era. Modern engineers have reverse-engineered these devices and found them shockingly effective. In one test, a replica Egyptian lock resisted picking attempts for over 30 minutes, while a medieval ward lock was breached in under 2. The secret, the pin's reliance on gravity, meant they couldn't be jiggled or forced like later designs. Even the keys were innovative, often shaped like toothbrushes with pegs. They doubled as portable status symbols. Wealthy Egyptians wore them as necklaces, a Bronze Age version of flashing your car fob. Yet, like many ancient innovations, this technology faded before being rediscovered. The pin tumbler lock wouldn't resurface until the mid-19th century, when Linus Yale Jr. patented his modern metal version. Today, over 90% of cylinder locks worldwide trace their lineage directly to those Nile Valley prototypes. So next time you turn a key, remember, you're not just unlocking a door, you're completing a ritual that began with Egyptian artisans carving wood under the desert sun. And as we close this chapter on ancient security, our journey takes us to the bustling markets of Rome, where fast food wasn't a modern invention, it was a 2,000-year-old innovation. Shifting our gaze from the sands of Egypt to the ancient halls of China, we encounter another marvel that bridges past and present: the legendary seismograph of Zhang Heng. Invented in the 2nd century during the Han Dynasty, this ingenious device wasn't just ahead of its time. It was so advanced that modern scientists have spent years trying to replicate its precision. Zhang Heng's seismograph was a masterpiece of engineering and artistry. Picture a large bronze vessel adorned with 8 dragon heads, each holding a metal ball in its jaws. Below them sat 8 corresponding toads with their mouths open, ready to catch any falling balls. At the slightest tremor, the dragon facing the earthquake's direction would release its ball into the toad's mouth, pinpointing the quake's origin with eerie accuracy. Historical records claim it detected an earthquake over 100 miles away, a feat that stunned the emperor's court, as no one in the capital had felt the tremor yet. For centuries, scholars debated whether the device truly worked or was merely a symbolic artifact. The original design was lost to time, leaving only cryptic descriptions in ancient texts. But in 2005, a team of Chinese and European scientists took on the challenge of recreating it, determined to settle the debate. Their goal wasn't just historical curiosity. They wanted to see if a 2,000-year-old mechanism could outperform modern seismometers in certain ways. The reconstruction revealed astonishing details. The team discovered that the secret lay in the pendulum hidden inside the vessel. When tremors struck, the pendulum would sway, triggering a lever system that released the dragon's ball. But here's the genius part: the design was sensitive enough to filter out minor vibrations like footsteps or carts, responding only to genuine seismic waves. Modern tests showed it could detect quakes as low as magnitude 4, even at distances modern instruments struggle with. One of the most dramatic validations came in 2008, when a replica seismograph was placed in a lab alongside state-of-the-art digital sensors. During a simulated quake, both devices registered the event within seconds, but the ancient design had one unexpected advantage. While modern seismometers require power and complex algorithms to interpret data, Zhang Heng's device gave an immediate visual alert. No electricity, no wires, just pure mechanics doing the job. Beyond its technical brilliance, the seismograph's revival highlights a deeper truth. Many ancient inventions weren't just lucky guesses, they were built on meticulous observation and problem-solving. Zhang Heng, a polymath who also excelled in astronomy and mathematics, likely studied years of earthquake patterns before refining his design. His work mirrors modern seismology's principles, just without today's technology. Today, replicas of the seismograph are displayed in museums worldwide, not just as relics but as tributes to human ingenuity. Some engineers are even exploring whether its passive, energy-free design could inspire disaster warning systems in remote areas. Imagine a low-cost, maintenance-free device helping villages detect quakes just as it did 2 millennia ago. As we marvel at this blend of art and science, our journey takes us next to the roaring battlefields of Byzantium, where fire itself became a weapon. One so terrifying its recipe was deliberately erased from history. Now let's step onto the ancient superhighways of Rome, roads so masterfully engineered that many are still in use today, 2,000 years later. While modern cities struggle with potholes and crumbling asphalt, the Romans built pathways that defied time, connecting an empire stretching from Scotland to Syria. Their secret wasn't just brute force or slave labor. It was a revolutionary approach to design, materials, and foresight that modern engineers still study in awe. Picture a Roman road, not a dirt trail or cobblestone lane, but a multi-layered masterpiece. First, workers dug a trench 3 to 5 feet deep, packing the base with crushed stone or sand to prevent shifting. Next came layers of gravel, cemented with lime mortar, followed by hand-cut volcanic rock slabs fitted together like a puzzle. But the true genius was the road's camber, a slight upward curve in the center that allowed rainwater to drain into ditches flanking either side. No more washed-out roads or muddy quagmires. These highways stayed dry and intact, even under torrential rains or the constant grind of iron-wheeled carts. One of the most staggering examples, the Appian Way, built in 312 BC and still partially walkable today. Stretching over 350 miles from Rome to Brindisi, it was the empire's lifeline, moving troops, goods, and ideas at unprecedented speeds. Messengers could cover 50 miles a day, a blistering pace for the ancient world thanks to the road's flawless gradient, which rarely exceeded an 8% slope even over hills. Modern surveys using laser technology reveal how Roman engineers carved through mountains or bridged marshes with precision rivaling today's GPS-guided machinery. But durability wasn't the only innovation. The Romans embedded milestones along every major route, stone markers noting distances to the nearest town, rest stops, and even roadside inns. It was the ancient equivalent of highway signage and service plazas combined. Some milestones even bore political messages, turning roads into propaganda tools. Imagine driving down a modern interstate and seeing plaques boasting about the president's achievements. That was everyday life in Rome. What's even more remarkable is how these roads were maintained. Archaeologists have uncovered repair contracts etched into stone, showing that local communities were legally obligated to upkeep sections of road, a system echoing modern municipal responsibilities. The Romans also understood the value of standardization. Their roads were consistently 24 Roman feet wide, about 23 modern feet, allowing 2 chariots to pass comfortably. This uniformity enabled trade and military movement across continents without constant adjustments for varying road widths. The legacy of Roman roads isn't just historical trivia. Modern highway designs, from the autobahns of Germany to the U.S. interstate system, borrow directly from their techniques. The aggregate base method, layering crushed stone beneath pavement, is a Roman innovation. Even the word highway traces back to the Latin via alter, meaning highway, referencing the raised construction that kept roads above flood levels. Yet perhaps the most poignant testament to Roman engineering lies in the shadows of these roads. Recent excavations have uncovered wear marks from chariot wheels, grooves worn by millions of footsteps, and even ancient graffiti scratched into stones by travelers. These roads weren't just infrastructure, they were the veins of an empire pulsing with the lives of countless people. Today, as we drive on highways that crumble after a decade, it's humbling to walk on Roman pavement that has endured millennia. From roads that united an empire, we turn next to a device that conquered time itself, the intricate water clocks of ancient Greece, where the flow of a single drop could measure the hours with uncanny precision. Moving from the grand highways of Rome, let's step into a more intimate but no less ingenious invention, an ancient Greek gadget that brought automation to the art of hospitality. Meet Philo of Byzantium's automatic wine pourer, a marvel of hydraulics and mechanics that could mix wine and water with the flick of a lever, like a proto-cocktail machine from the 3rd century B.C. Imagine hosting a lavish Greek symposium where wine flowed freely, but not recklessly. The Greeks famously diluted their wine with water, a practice tied to both cultural refinement and practical sobriety. But manually mixing the perfect ratio was tedious. Enter Philo, a brilliant engineer whose device took the guesswork out of the process. His invention was a vessel with 2 compartments, one for wine, one for water, connected by a series of tubes and valves. When a guest placed their cup under the spout and pressed a lever, the machine released precise amounts of both liquids simultaneously, blending them instantly. No overpouring, no uneven mixes, just a perfectly balanced drink every time. The mechanism relied on basic but clever physics. The compartments were sealed to maintain pressure, and the valves were calibrated to control flow rates. Some reconstructions suggest it even used a floating device like a cork to regulate the mixture based on how much liquid remained. This wasn't just a party trick, it was an early example of feedback-based automation, a principle now found in everything from espresso machines to industrial robotics. But Philo's device had a deeper purpose. In Greek culture, the ritual of mixing wine and water was symbolic. Undiluted wine was considered barbaric, while the right ratio reflected moderation and intellect. By automating this, the wine pourer didn't just save time, it upheld social norms with mechanical precision. Some historians speculate that the device might have even been used in temples where consistency in ritual offerings was sacred. What's astonishing is how this ancient gadget mirrors modern conveniences. Think of today's soda fountains where a single button dispenses a pre-mixed drink, or smart coffee makers that adjust water to coffee ratios digitally. Philo's invention was a mechanical ancestor of these systems, proving that even 2,000 years ago, humans sought ways to streamline daily rituals without sacrificing quality. Surviving descriptions of the device are sparse, but modern engineers have recreated it based on Philo's writings. Functional replicas confirm it worked exactly as described, no magic, just ingenuity. And Philo didn't stop there. His portfolio included pneumatic door openers, alarm clocks, and even a self-regulating oil lamp. He was a pioneer of automation, a field we often associate with the Industrial Revolution or Silicon Valley, not ancient Alexandria. Yet for all its brilliance, the automatic wine pourer raises a tantalizing question. Why didn't this spark a broader wave of automation in antiquity? The answer lies in context. While ingenious, these devices were costly novelties for elite gatherings, not mass-produced tools. Without the infrastructure to scale them, they remained curiosities rather than revolutions. But their legacy lingers. Every time you use a touchless faucet or a drink dispenser, you're interacting with a descendant of Philo's vision, a reminder that the past's toys often seed the future's necessities. From the symposiums of Greece, we'll next unravel a device that turned knotted strings into a language, the Inca quipu, a binary-like record system that some argue rivaled the written word. Now, let's unravel a mystery that stretches across the Andes, a communication system not of ink and paper, but of knots and cords. The Inca quipu was a dazzlingly complex tool, a network of colored strings tied in precise patterns that recorded everything from census data to epic poetry. Imagine a civilization running an empire spanning 2,000 miles without a single written word, relying instead on these tactile, almost musical strands to keep its vast bureaucracy humming. At first glance, a quipu might resemble a fringe decoration, pendant cords dangling from a main rope, each with clusters of knots, but every element was deliberate. The colors of the strings, their placement, the types of knots, even the direction the knots were tied, all held specific meanings. Some cords recorded numbers using a base 10 system, with knot clusters representing units, tens, hundreds. Others conveyed narratives, possibly even histories or laws, through symbolic patterns we're still struggling to fully decipher. What's staggering is the scale. The Inca Empire used quipus to track taxes, military logistics, and astronomical cycles across territories larger than the Roman Empire. Spanish chroniclers noted that official quipu readers, called quipucamayocs, could recount exact details from decades past by reading these knots, much like a librarian pulling a book from a shelf. One account describes a quipucamayoc reciting a land dispute's verdict from 20 years earlier, with the knots confirming names, dates, and quantities owed. But here's the twist: quipus weren't just spreadsheets. Recent research suggests some may have encoded phonetic sounds or syllables, blurring the line between accounting and actual writing. Harvard anthropologist Gary Urton proposed that the knots combinations might function like a binary code, similar to the ones and zeros in modern computing. If true, this would make quipus one of the few three-dimensional writing systems in history, a language you could touch, tied into existence. Why does this matter today? Because it challenges a deep-seated bias that advanced cultures must have alphabets. The Inca built Machu Picchu, engineered terraces that resisted earthquakes, and knitted suspension bridges from grass, all without formal writing as we know it. The quipu proves that intelligence isn't bound by scripts. It's a reminder that innovation wears many faces, yet the system's fragility is heartbreaking. After the Spanish conquest, quipus were banned as idolatrous, and most were burned. Only about 1,000 survive, many in fragments. modern scholars are racing to decode them, using everything from databases to AI pattern recognition. In 2021, a team at the University of St. Andrews even trained machine learning to analyze knot arrangements, hoping to crack their secrets. What's tantalizing is what we've glimpsed so far. Some quippers appear to map lunar cycles, others may encode songs or myths. There's evidence they were used for democratic voting, villages tying knots to signal consensus. And intriguingly, quipukamayaks in remote Andes villages still use descendant systems today, tracking livestock with knots, a thread of knowledge stretching unbroken across 5 centuries. This isn't just ancient tech, it's a different way of thinking. Where we default to pixels and paper, the Inca built a language of texture and rhythm where math and story intertwined. Every quipu was a ledger, a poem, and a contract all tied into one. And that's a lesson for our digital age. Information doesn't need screens to be sophisticated. Sometimes it just needs a string and a knot. From the woven languages of the Andes, we'll next turn to the stars specifically. The Babylonian tablets that tracked Jupiter's path with math so advanced, it predated European calculus by millennia. Now let's leap across continents and centuries to the dusty clay tablets of ancient Babylon, where astronomers etched celestial secrets with a precision that would stump European mathematicians for millennia. These weren't just star charts, they were sophisticated mathematical diaries, tracking Jupiter's path across the night sky using geometric techniques eerily similar to modern calculus. Picture this: around 350 BC, Babylonian scribes huddled under the Mesopotamian night, meticulously recording Jupiter's position night after night. But they didn't just note its movements, they calculated its speed and predicted its future path using a method called trapezoidal area analysis. Essentially, they broke Jupiter's journey into segments, plotting time against distance, then calculated the area under these curves to determine its velocity, a technique that wouldn't emerge in Europe until the 14th century. What's astonishing is how practical their astronomy was. These tablets, known as ACT 837, weren't philosophical musings, they were tools for agriculture, taxation, and even omens. The Babylonians believed planetary motions influenced earthly events, so predicting Jupiter's path wasn't just academic, it dictated when to plant crops or levy taxes. Their math was so advanced that modern scholars like Matthew Ossendraver of Humboldt University spent years deciphering their methods. In 2016, he made a breakthrough. The tablets weren't just tracking Jupiter, they were modeling its acceleration, a concept Europe wouldn't formalize until Newton. But here's the twist: the Babylonians didn't have telescopes or even a heliocentric model of the solar system. They worked purely from naked eye observations, using iterative arithmetic, a bit like solving a puzzle by trial and error, to derive their formulas. Their calculus was baked into clay, not penned in textbooks, yet it achieved accuracies within 10% of modern calculations. Why does this matter? Because it rewrites the timeline of mathematical innovation. While we credit 17th century Europeans like Leibniz and Newton for calculus, these tablets prove the groundwork was laid over 1,500 years earlier in the cradle of civilization. The Babylonians didn't just observe the stars, they mathematized them, treating the sky as a cosmic ledger. Yet their brilliance had limits. Their math was purely utilitarian, no theoretical framework, no grand unified laws. They solved problems without asking why the solutions worked. It's like having a GPS that guides you flawlessly without explaining how it calculates the route. Today, these tablets are more than relics, they're a testament to how observation and necessity breed innovation. The Babylonians didn't have our technology, but their intellectual curiosity and their knack for turning clay into data rivals any modern algorithm. As we move from celestial math to mechanical might, keep this in mind. Sometimes the oldest tools hold the sharpest insights. Next, we'll delve into a cosmetic innovation that doubled as ancient medicine. the Egyptian eyeliner that fought infections while accentuating beauty. Now, let's shift our gaze from the stars to something far more personal, the mirrors of ancient Egypt, where beauty and science intertwined in ways that still leave modern researchers stunned. Picture the banks of the Nile over 4,000 years ago, where both men and women lined their eyes with thick, dramatic kohl, not just for allure but for survival. What seemed like mere cosmetics were actually early medical marvels. The Egyptians crafted their iconic black eyeliner from a mixture of galena, a lead-based mineral, and other natural ingredients like crushed malachite and charcoal. At first glance, lead in makeup sounds like a recipe for disaster. After all, we know now how toxic it can be. But here's the twist: in tiny, controlled doses, their formula had surprising benefits. Modern lab tests, including a groundbreaking 2010 study by French chemists, revealed that the lead compounds in Egyptian kohl triggered a chemical reaction in skin cells. This reaction produced nitric oxide, a molecule that supercharges the immune system, helping ward off eye infections rampant in the marshy Nile Delta. Think of it as an ancient antibiotic, delicately applied with a polished stick of ivory or wood. The same lining that accentuated the almond shape of their eyes also protected them from trachoma, a bacterial disease that still blinds millions in arid regions today. The precision of their recipes is equally striking. Archaeologists have found pots of kohl in tombs with labels specifying ingredients and proportions, some even noting which mixtures were for daily wear versus sacred rituals. One particularly potent blend, reserved for pharaohs and priests, contained trace amounts of copper oxide, adding an extra antimicrobial punch. It's as if they'd cracked the code for preventive medicine millennia before germ theory. But the innovation didn't stop at health. The Egyptians understood optics too. The dark kohl reduced glare from the sun, much like the black grease modern athletes smear under their eyes. For a civilization that worshipped the sun god Ra, this wasn't just practical, it was divine pragmatism. Even their makeup tools were engineered for precision, with applicators tapered to create the perfect cat eye effect depicted in hieroglyphs. Why does this matter today? Because it shatters the assumption that ancient medicine was purely superstition. The Egyptians didn't just stumble upon these properties, they observed, experimented, and refined their recipes over centuries. Their kohl wasn't merely decorative, it was pharmacology in action, a fusion of beauty and biology that predated modern cosmeceuticals by millennia. As we move from the elegance of Egyptian cosmetics to the roar of Byzantine warfare, remember, sometimes history's most potent secrets are hidden in the smallest details, even in the stroke of an eyeliner brush. Next, we'll ignite the story of Greek fire, a weapon so fearsome its recipe was worth more than gold. Now, let's journey from the banks of the Nile to the bustling shores of ancient Carthage, where a different kind of alchemy turned the humble sea snail into a symbol of power and prestige. Imagine a color so rare, so vibrant, that wearing it could elevate you above kings. This was Tyrian purple, the jewel of Carthaginian industry. The process began with tens of thousands of murex sea snails harvested from the Mediterranean's depths. Each snail secreted just a single drop of precious liquid, a milky goo that transformed into a deep, luminous purple when exposed to sunlight. But here's the catch: producing enough dye for a single robe required crushing up to 12,000 snails. That's an entire beach's worth of mollusks for one garment. What made Tyrian purple so coveted wasn't just its beauty, it was chemistry perfected over centuries. Carthaginian dye factories, some spanning acres along the coast, mastered a fermentation technique to intensify the color. The snail glands were soaked in lead vats filled with salt water for days, allowing enzymes to work their magic. The result, a shade that didn't fade even after decades in the sun. Modern tests show it resisted light damage better than many synthetic dyes invented in the 19th century. The industry's scale was staggering. Archaeologists have found heaps of broken shells near ancient Carthage, some piles towering over 30 feet high, evidence of a production line rivaling modern factories. Workers labored in shifts, extracting glands around the clock to meet demand from Rome to Persia. The stench of rotting shellfish was so potent that dye districts were built downwind of cities, yet the end product was worth its weight in silver. Tyrian purple's exclusivity shaped history. Roman emperors, desperate to flaunt their status, passed sumptuary laws reserving the color for royalty. Wearing unauthorized purple could cost you your life. But Carthage's monopoly didn't last forever. When Rome destroyed the city in 146 BC, they looted not just gold but vats of dye, dragging Carthaginian dyers back to Italy as slaves to keep the industry alive. Why does this matter today? Because Carthage's dye factories were more than just workshops, they were early chemical plants, combining biology, metallurgy, and mass production. Modern fashion brands still chase that elusive, perfect color, spending millions on synthetic dyes, yet none have quite matched Tyrian purple's mystique. It's a reminder that ancient luxury wasn't just about opulence, it was a high-stakes science where the line between a rotting snail and a king's robe was thinner than you'd think. Next, we'll ascend from the dye vats of Carthage to the skies of ancient China, where paper lanterns weren't just decorations, they were the world's first hot air balloons. Let's lift our gaze from the bustling dye workshops of Carthage to the tranquil skies of ancient China, where ingenuity took flight in the most unexpected way. Centuries before the Montgolfier brothers made history with their hot air balloon in 18th century France, the Chinese were already mastering the art of aerial signaling with a device as elegant as it was ingenious, the Congming lantern. These delicate paper lanterns, named after the legendary strategist Zhuge Liang, also known as Congming, weren't just for festivals. They were early tools of communication and even psychological warfare. Picture this, a lightweight bamboo frame covered in thin paper with a small wax or oil lamp at its base. When lit, the flame heated the air inside, causing the lantern to rise gracefully into the night sky, glowing like a floating ember. Armies used them to send signals across vast distances, their silent ascent cutting through the darkness to coordinate movements or mark positions. But the real marvel lies in the science behind their flight. The Congming lantern operates on the same principle as modern hot air balloons' buoyancy created by heated air. The Chinese didn't just stumble upon this idea, they understood the thermodynamics centuries before the term even existed. By controlling the size of the lantern and the intensity of the flame, they could dictate how high it soared and how long it stayed aloft. Some historical accounts suggest these lanterns could remain airborne for hours, drifting for miles before the flame exhausted its fuel. What's even more fascinating is how they were adapted for warfare. During the Three Kingdoms period, Congming allegedly used clusters of these lanterns to create the illusion of celestial intervention, intimidating enemy troops who mistook them for supernatural omens. Imagine hundreds of fiery orbs ascending in unison, a spectacle designed to unsettle even the bravest soldiers. It was ancient psychological ops, blending technology and theater to devastating effect. The legacy of the Congming lantern extends far beyond the battlefield. Today, they're celebrated in festivals across Asia, their peaceful glow a far cry from their martial origins. Modern engineers even study their design to refine drone technology and emergency signaling devices. Yet, for all our advancements, there's poetry in the fact that one of humanity's earliest forays into controlled flight relied on nothing more than paper, fire, and a profound understanding of the wind. From the battlefields of ancient China to the quiet glow of modern celebrations, the Congming lantern reminds us that sometimes the simplest ideas defy time. And speaking of defying expectations, wait until you hear how the Greeks turned water pressure into musical precision, but that's a story for another moment. Now let's journey from the glowing skies of ancient China to the sun-drenched workshops of Greece, where another brilliant mind was redefining time itself. While today we tap our smartphones to silence a blaring alarm, the ancient Greeks had a far more elegant and liquid solution to waking up on time. Enter Ctesibius, a 3rd century BC inventor whose water clock didn't just measure hours, it announced them with the chime of a bell, making it the world's first mechanical alarm clock. At first glance, Ctesibius' device might seem like just another water clock or clepsydra, a common tool in antiquity for tracking time. But his genius lay in the added mechanism that transformed it into something revolutionary. Here's how it worked. Imagine a large vessel filled with water dripping at a steady rate into a second container. As the water level rose in this second chamber, it lifted a float attached to a rod. At a predetermined height, say, the crack of dawn, the rod would trigger a lever, releasing a cascade of pebbles or metal balls onto a bronze gong. The result? A sudden, unmistakable clang to rouse sleepers, proving even ancient Greeks struggled with mornings. What's remarkable is the precision behind this design. Ctesibius didn't just invent an alarm, he engineered a system adjustable to different wake-up times. By altering the water flow or the position of the trigger rod, users could set the alarm for shorter or longer durations. Some historians speculate that variations of this clock might have been used in temples to signal prayer times or in cities to coordinate civic events. Think of it as the ancient equivalent of setting multiple alarms for work, gym, and that important meeting, only with more hydraulics and fewer snooze buttons. But Ctesibius didn't stop there. His water clock was part of a broader fascination with automation, a field where the Greeks were centuries ahead of their time. The same principles of water pressure and mechanical triggers appeared in his other inventions, like self-playing organs and even animated statues. It's a reminder that the line between practical tools and playful ingenuity was often blurred in antiquity. Fast forward to today, and you'll see Ctesibius' legacy in everything from the ticking gears of grandfather clocks to the digital alarms on our nightstands. Modern engineers still study his designs for their elegant simplicity and reliability. After all, while our smartphones might have replaced water-powered alarms, the core idea remains unchanged, a device that tells us when to wake up, work, or worship. So the next time you groan at your morning alarm, spare a thought for Ctesibius and his ancient innovation. Because whether it's water or Wi-Fi, humanity's quest to master time and our own schedules has always been a race against the clock. And speaking of races, our next invention takes us to the battlefields where the Greeks turned pressure into another kind of power, one that could hurl stones with terrifying accuracy. But that's a story for another moment. But let's not leave the ancient world just yet, because while Ctesibius was perfecting timekeeping, the Romans were mastering another craft that would change how we see the world, quite literally. Imagine holding a piece of glass so finely crafted it could bend light, magnify text, or even correct vision. That's exactly what Roman artisans achieved with their groundbreaking grooved glass, an innovation that laid the foundation for modern optics. These weren't just decorative trinkets. The Romans developed a meticulous technique for carving precise, concentric grooves into glass surfaces, creating lenses capable of focusing light. Picture a shallow glass bowl or disc, its surface etched with carefully spaced ridges radiating outward like ripples in a pond. When light passed through these grooves, it refracted, bending in a way that could magnify objects or project sharper images. This wasn't just artistry, it was applied physics centuries before scientists formalized the laws of optics. Archaeologists have unearthed Roman grooved glass fragments across the empire from Britain to Egypt. Some were clearly used as burning lenses, harnessing sunlight to ignite fires, a practical tool for soldiers and craftsmen. Others, like the famous Nimrod lens, though Assyrian, it shares similarities with Roman designs, hint at even more sophisticated applications. Historians speculate that these lenses might have aided jewelers in intricate engraving or helped scholars scrutinize tiny text on scrolls. Could they have been the first spectacles? While evidence is scarce, the principle was there, manipulating light to serve human needs. What made Roman grooved glass remarkable was its precision. Without modern grinding tools, artisans relied on handheld abrasives and painstaking patience to carve each groove at consistent depths and spacing. Experiments recreating these lenses show that even minor errors in spacing could scatter light instead of focusing it. Yet surviving examples prove the Romans achieved near-perfect symmetry, suggesting standardized techniques or even early workshops dedicated to lens making. The legacy of this ingenuity is everywhere today. Those grooves were the ancestors of modern eyeglass lenses, camera optics, and even the fiberglass cables that power our internet. When you adjust your prescription glasses or zoom in with your smartphone camera, you're using principles the Romans fiddled with over 2,000 years ago. Their work reminds us that innovation isn't always about inventing something entirely new. Sometimes it's about refining an idea until it changes everything. And refinement was something the Romans excelled at, whether in glass, warfare, or even metallurgy, which brings us to our next marvel. Because while lenses helped people see better, another ancient innovation helped them cut deeper. Damascus Steel, a metal so sharp and strong its secrets sparked obsession for centuries. But that's a story for another moment. Now let's turn our attention to another ancient marvel that reshaped the world, this time not through glass or optics but through fire and metal. Deep in the heart of ancient India, blacksmiths and metalworkers achieved something extraordinary. They built furnaces so advanced they could produce steel rivaling the finest alloys of today. These weren't just simple kilns, they were engineering marvels capable of reaching temperatures that would astonish even modern metallurgists. The secret lay in their design. Known as wind or air furnaces, these structures stood tall, often reaching heights of over 6 feet, with carefully designed air vents at the base. By harnessing natural wind patterns or using bellows, these furnaces could channel oxygen into the burning charcoal, stoking the flames to blistering temperatures. Some estimates suggest they exceeded 1,200 degrees Celsius. That's hot enough to melt iron and purify it into high-carbon steel, a material prized for its strength and flexibility. What's truly remarkable is how these ancient smiths controlled the process. They didn't have digital thermometers or precision tools, yet they mastered the art of temperature regulation by adjusting airflow and fuel. Archaeologists have found remnants of these furnaces scattered across India, particularly in regions like Telangana and Tamil Nadu, where iron ore was abundant. The slag, waste material left over from smelting, shows a consistent, high-quality output, proving these weren't just experimental setups but large-scale production sites. The steel produced in these furnaces wasn't just ordinary metal. It became famous across the ancient world, traded as far as Rome and Damascus. One of its most celebrated uses was in the creation of wood steel, a type of crucible steel known for its distinctive watery or swirling pattern. When forged into blades, this steel was legendary. It could hold an edge sharper than most modern knives while remaining resilient enough to withstand heavy blows. European traders who encountered it in the Middle Ages called it Damascus Steel, though its true origins lay in these Indian furnaces. But how did they achieve such consistency without modern technology? The answer lies in their deep understanding of materials. They mixed specific types of iron ore with carbon-rich organic matter, like leaves or wood, creating a chemical reaction that removed impurities. The result was a nearly homogeneous steel with tiny carbon nanotubes, a nanostructure modern scientists only identified with electron microscopes. These microscopic formations gave the steel its legendary durability, a feature researchers are still trying to replicate today. The legacy of these furnaces is undeniable. They produced tools and weapons that shaped empires, from the Mauryan dynasty's agricultural implements to the swords of the Mughal warriors. Even now, metallurgists study these ancient techniques for clues on sustainable steel production. While today's factories rely on coke and electric arcs, these furnaces used renewable charcoal and clever engineering, offering lessons in efficiency that resonate in our eco-conscious age. As we marvel at these achievements, it's clear that ancient India's metalworkers were far ahead of their time. But our journey through history's greatest inventions isn't over yet, because next we'll explore a taste of the ancient world that still delights us today: the Mayans' mastery of chocolate, a treat as complex as it was delicious. Moving from the blazing heat of ancient furnaces to the lush rainforests of Mesoamerica, we uncover another masterpiece of early innovation, this time not in metal but in flavor. The Mayans didn't just consume chocolate, they perfected it through a series of intricate chemical processes that transformed bitter cacao beans into a luxurious, frothy drink centuries before Europe even knew it existed. The journey began with the cacao tree, a plant the Mayans revered as sacred. They harvested its pods, but unlike today's quick chocolate bars, their process was a slow, deliberate alchemy. First came fermentation. The beans, still coated in sweet, pulpy flesh, were piled into wooden boxes or buried in leaf-lined pits. Over several days, natural microbes worked their magic, breaking down the pulp and initiating biochemical changes within the beans. This step was crucial. It eliminated the raw bitterness and unlocked the rich, complex flavors we associate with chocolate today. Without it, chocolate would taste harsh and acidic. Next, the beans were roasted over gentle fires, a step modern chocolatiers still use. But here's where the Mayans diverged. They didn't just roast them. They infused the beans with smoky depth by adding spices like vanilla or chili to the fire. Once roasted, the shells were removed, and the nibs, the heart of the bean, were ground into a paste using stone tools called metates. This wasn't mere crushing. It was a rhythmic, hours-long process that released cocoa butter, creating a smooth, velvety texture. Now came the true artistry. The Mayans mixed this paste with water, not milk, and poured it repeatedly between vessels to aerate it, creating a frothy foam they considered the most divine part of the drink. They believed this foam carried the spirit of the cacao god, Ecchua. To enhance the flavor, they added ingredients like honey, ground maize, or aromatic flowers, crafting a beverage that was both energizing and ceremonially significant. What's astonishing is how scientifically advanced their methods were. Fermentation, which they mastered empirically, generates the very compounds like phenylethylamine that give chocolate its mood-boosting properties. Their grinding technique, though labor-intensive, preserved the cocoa's natural fats, avoiding the waxy texture of poorly processed chocolate. Even their serving temperature was precise, cool for daily consumption, warm for rituals. European colonists later sweetened and simplified the recipe, but the Mayan legacy endures. Modern craft chocolatiers now replicate their methods, praising the depth of flavor achieved through traditional fermentation and stone grinding. And let's not forget, this was more than a drink. Cacao beans were currency, a ritual offering, and a bridge between earthly and divine realms. So the next time you savor a piece of chocolate, remember, you're tasting a recipe refined over millennia, a testament to the Mayans' ingenuity. And speaking of recipes, our next discovery takes us to the windswept deserts of Persia, where ancient engineers turned breezes into air conditioning, but that's a story for later. From the rich flavors of Mayan chocolate, let's journey to the arid landscapes of ancient Persia, where engineers turned the desert's relentless heat into a cool oasis, no electricity required. The Persians mastered passive cooling long before modern air conditioning, and their secret weapon was the wind catcher, a towering architectural marvel that harnessed nature's breezes to create comfortable indoor spaces even in scorching summers. Imagine a soaring brick chimney rising from a building's roof, its top slit into multiple openings facing different directions. That's the wind catcher, or badger in Persian. Designed over 2,000 years ago, these structures worked like natural HVAC systems. Here's the genius: as wind blew across the desert, it entered the tower's openings. The air funneled downward through narrow shafts would speed up and cool slightly due to pressure changes, a principle now known as the Venturi effect. But the real magic happened underground. The shafts connected to qanats, subterranean water channels that further chilled the air through evaporation. By the time the breeze reached the living spaces below, it was refreshingly cool. What's even smarter, wind catchers had adjustable vents. If the wind was dusty or too hot, residents could close certain openings to redirect airflow. Some designs even included wet cloths or ceramic water jars at the base to add moisture, enhancing the cooling effect. A crude but effective ancient humidifier. And on stifling days with no breeze, the tower acted in reverse. Hot indoor air rose and escaped through the top, drawing cooler air from the qanat tunnels below. The impact was profound. Cities like Yazd and Kashan, where temperatures could soar past 120 degrees Fahrenheit, thrived thanks to wind catchers. Homes, mosques, and even ice houses, yes, they stored ice in the desert, stayed bearable year-round. The system was so efficient that some historic buildings still use their original wind catchers today, outperforming modern electric coolers in sustainability. Modern architects are now rediscovering this ancient tech. Passive cooling principles from wind catchers inspire green buildings worldwide, from Dubai's eco-towers to experimental designs in Arizona. Researchers estimate that properly designed wind catchers can lower indoor temperatures by up to 20 degrees, slashing energy use. It's a reminder that sometimes the best solutions aren't high-tech, they're timeless. So next time you adjust your thermostat, spare a thought for the Persian engineers who tamed the desert with nothing but brick, wind, and ingenuity. And if you think that's clever, wait until we explore how the Egyptians built ships so sturdy. They sailed smoothly 1,000 years after their creation, but that's a tale for another moment. Now let's set sail from Persia's wind-cooled deserts to the banks of the Nile, where the ancient Egyptians mastered shipbuilding with techniques so advanced, their vessels outlasted civilizations. Picture this, a fleet of wooden ships gliding down the Nile, their hulls so tightly joined that they remained seaworthy for centuries. This wasn't luck, it was the brilliance of mortise and tenon construction, a method so effective that modern shipwrights still study it today. Unlike simple nails or ropes, the Egyptians carved interlocking joints into each plank, fitting them together like a 3D puzzle. The mortise, a slot cut into one plank, would snugly receive the tenon, a protruding tongue from another. These joints were then sealed with pegs or natural adhesives, creating a hull that flexed with the waves without cracking apart. But here's what made it revolutionary. While other cultures lashed boats together with fibers that rotted over time, Egyptian ships grew stronger with age. The mortise and tenon system distributed stress evenly across the hull, preventing weak points. Archaeologists found a stunning example in the Khufu ship, buried near the Great Pyramid around 2500 BCE. When reassembled after 4.5 millennia, its planks still locked together perfectly, no gaps, no warping. Imagine building something so precise that it survives longer than the languages spoken by its creators. The Egyptians didn't stop there, they treated their ships like living things. Hulls were coated in resin or tar to repel water, while internal ribs reinforced the structure, a precursor to modern framing. Some vessels even had removable masts and adjustable sails, allowing them to navigate both the Nile's gentle currents and the Mediterranean's open waters. These weren't just river barges, they were blue water marvels. The famed Byblos ships, which traded cedar with Lebanon, routinely braved hundreds of miles of open sea, a testament to their durability. And here's a twist, these ships saved lives long after their era. When the Romans invaded Egypt, they found Nile ships still in use from the New Kingdom period, nearly 1,000 years earlier. Instead of building new fleets, the Romans simply refurbished the existing ones. That's like using a car from the Middle Ages to commute today, even more astounding. The Tanjara, a reconstructed pharaonic ship, proved its seaworthiness in modern tests, sailing the Red Sea with ease. So why did this technology fade? Blame economics, not engineering. Mortise and tenon construction was labor-intensive, requiring skilled artisans and time. When Rome industrialized shipbuilding, they prioritized speed over longevity, opting for faster, cheaper methods. But the lesson remains. The Egyptians understood that great design isn't about shortcuts, it's about crafting for eternity. Next time you marvel at a modern cruise ship scale, remember the quiet genius of those ancient hulls built to outlast dynasties. And speaking of endurance, wait until we uncover how the Chinese turned a simple cabinet into a flamethrower that terrified entire armies. A story where fire meets ingenuity in the most explosive way. Now, let's shift from the sturdy ships of the Nile to the fiery battlefields of ancient China, where warfare took a terrifying turn with a weapon straight out of a nightmare: the fierce fire oil cabinet. Imagine standing on a medieval battlefield, watching as enemy soldiers wheel forward what looks like an ornate wooden chest. Then, with a sudden roar, a jet of liquid fire erupts, engulfing everything in its path. This wasn't just any flamethrower, it was a precisely engineered horror capable of spraying burning oil over dozens of feet. The Chinese didn't just invent gunpowder, they perfected the art of fire itself, turning it into a weapon of mass destruction centuries before the modern world caught up. At the heart of this device was a deceptively simple mechanism. The fierce fire oil cabinet used a double-action piston pump, likely made of bronze or iron, to pressurize a reservoir of highly flammable oil, often a mix of petroleum, sulfur, and saltpeter. When a soldier cranked the pump's handle, the oil would shoot through a narrow tube, ignited by a slow-burning fuse at the nozzle. The result: a continuous stream of fire that could sweep across fortifications or enemy lines, clinging to skin and armor alike. But here's what made it so devastating. It wasn't just a glorified torch. The Chinese optimized the chemistry of their fuel to burn hotter and longer than anything Europe had seen. Historical texts describe mixtures that included quicklime, which reacts violently with water, making it impossible to extinguish with conventional methods. Some accounts even mention additives like ground porcelain or iron shavings, creating a napalm-like effect that stuck to targets and burned for minutes. One of the most infamous uses of this weapon was during the Siege of Dan in the year 1132, where Song dynasty forces employed it against invading Jurchen troops. As the Jurchen scaled the city walls, defenders unleashed the fierce fire oil cabinet, turning the climbers into human torches. The psychological impact was as brutal as the flames. Soldiers reportedly fled in panic at the mere sight of the device being wheeled into position. Yet for all its terror, the flamethrower wasn't just about brute force. The Chinese integrated it into complex battlefield strategies. Some versions were mounted on wheeled carts, allowing rapid repositioning, while others were designed as stationary emplacements to defend gates or choke points. There's even evidence of naval variants, used to torch enemy ships by spraying fire across the water's surface, a tactic that predated Greek fire by centuries. So why didn't this technology dominate global warfare? The answer lies in its limitations. The fierce fire oil cabinet was expensive to produce, required skilled operators, and was dangerously unpredictable. A single spark in the wrong place could turn the weapon against its own users. Over time, as gunpowder weapons became more reliable, the flamethrower faded into obscurity, but its legacy lived on. Modern researchers have recreated the device using historical blueprints, confirming its terrifying efficiency. In controlled tests, the reconstructed flamethrower could project flames over 30 feet with a burn time exceeding 20 seconds. That's enough to break a siege or traumatize an entire army. This wasn't just a weapon, it was a statement. The Chinese understood fire's primal power and weaponized it with chilling precision. Next time you hear about flamethrowers in modern warfare, remember, The ancients did it first, and they did it with a level of ingenuity that still commands respect. And speaking of respect, few materials earned as much legendary status as the blades of Damascus Steel, swords so sharp and strong they seemed almost supernatural. But behind the myth lies a science even more fascinating. Now, let's leave the battlefields behind and step into a world where comfort and innovation merged in the most unexpected way: warm floors. Yes, you heard that right. Long before radiant heating became a modern luxury, the ancient Greeks were mastering the art of central heating in their grandest buildings, like the Temple of Ephesus. Picture this: it's a chilly morning in Ephesus, and instead of huddling around a fire, priests and worshippers walk barefoot across floors that are subtly, perfectly warm. How beneath their feet lies a network of terracotta pipes, snaking through the foundation like the veins of a giant. These weren't just crude channels for smoke, they were part of a sophisticated hypocaust system, a precursor to what we now call radiant heating. The genius of this setup was its simplicity. Fires were lit in a central furnace, often located in a basement or adjacent room. As the flames burned, hot air and smoke would travel through these carefully laid pipes, warming the terracotta tiles above. The tiles, in turn, radiated heat evenly across the floor, creating a consistent warmth without the need for open flames inside the living spaces. It was clean, efficient, and remarkably advanced for its time. But the Temple of Ephesus wasn't just about comfort, it was about precision. The pipes were designed with slight slopes to ensure smooth airflow, preventing backdrafts or cold spots. Some sections even had adjustable vents, allowing caretakers to control the temperature in different rooms. Imagine walking through a sacred space where the warmth underfoot was as carefully managed as the rituals taking place above. What's even more impressive is how this technology scaled. While the Romans later popularized hypocausts in their bathhouses, the Greeks had already perfected the basics. In Ephesus, the system wasn't limited to the temple nearby. Villas and public buildings also enjoyed this luxury. Archaeologists have found evidence of similar setups in private homes, suggesting that central heating wasn't just for the elite but a widespread innovation. Yet, like many ancient marvels, this technology faded with time. The fall of the Greco-Roman world saw hypocausts abandoned, and the knowledge of their construction was nearly lost. It wasn't until the 19th century that modern engineers rediscovered the principles of radiant heating, often reinventing what the Greeks had already mastered. Today, remnants of these systems still survive. In Ephesus, you can see the hollow spaces beneath the floors where the pipes once lay, a silent testament to an ingenuity that rivaled modern HVAC. Researchers have even recreated the system using original materials, proving that it could maintain a comfortable 22 degrees Celsius even in winter, a feat that would impress any modern homeowner. So the next time you adjust your thermostat, remember, the Greeks were there first, turning the very ground beneath their feet into a canvas for comfort and innovation. And speaking of innovation, few structures blended practicality and grandeur quite like the Roman fast food Thermopolia, ancient snack bars that catered to hungry crowds with shocking efficiency. Let's take a detour from grand temples and cozy floors to the bustling streets of ancient Rome, where convenience and flavor collided in a way that feels surprisingly modern. Picture this: it's midday in Pompeii and the city's workers are craving a quick, hot meal. But instead of swinging by a drive-through, they're lining up at Thermopolia, Rome's answer to fast food. These weren't just simple stalls. Thermopolia were the lifeblood of Roman urban culture, serving as the ancient equivalent of today's food courts. Built right into the street fronts, they featured long counters with deep, embedded clay pots called dolia. Inside these pots, dishes like spiced lentils, fish stew, or honey-glazed meat simmered over hot coals, ready to be scooped into portable bowls for hungry patrons on the go. The design was genius. The thick clay retained heat for hours, ensuring food stayed warm without constant reheating, a trick modern restaurants still use with heated trays and steam tables. But thermopolia weren't just about practicality. They were social hubs. Archaeologists have found over 80 of them in Pompeii alone, often decorated with vibrant frescoes of food and drink to entice customers. Imagine grabbing a steaming bowl of porridge under a painted mural of grapes and olives, chatting with neighbors about the latest chariot race. The menus were surprisingly varied too. Excavations revealed traces of everything from salted cheese and eggs to more exotic fare like dormice, a Roman delicacy. And yes, they even had a version of takeout, or wealthier households would send slaves to fetch meals from their favorite spots. What's fascinating is how these thermopolia mirrored modern dining trends. They catered to a fast-paced urban lifestyle, much like today's food trucks or coffee shops. Workers, shopkeepers, and even students relied on them for affordable, quick meals. The dolia's design also hints at early quality control. Their narrow openings minimized heat loss, while their depth kept flavors concentrated, much like a slow cooker. Some pots even had dual compartments, possibly for keeping sauces separate until serving a detail that wouldn't feel out of place in a modern kitchen. Yet thermopolia weren't without controversy. Elite Romans like Seneca sneered at them, calling the food vulgar and the crowds unruly, but their popularity was undeniable. In a city where many homes lacked kitchens, they were a necessity. And when Mount Vesuvius erupted, these snack bars became time capsules. Preserved under ash, some still held remnants of their last meals: walnuts, bread, even a fossilized loaf with a baker's stamp. Today, the legacy of thermopolia lives on. The next time you queue at a food truck or scan a menu board under neon lights, remember, the Romans were doing it 2,000 years ago, turning quick meals into a cultural experience. And as we wrap up our journey through these 50 ancient marvels, one thing's clear: innovation isn't just about the future. Sometimes it's about rediscovering the brilliance of the past. So, which of these ancient inventions amazed you the most? Drop your favorites in the comments, and don't forget to like and subscribe for more deep dives into history's hidden gems. Until next time, keep exploring, because the past is full of surprises waiting to be uncovered. Now, stepping back to take in the bigger picture, it's astounding how these ancient inventions shatter our modern assumptions about the past. For centuries, we've labeled early civilizations as primitive, but as we've seen, their ingenuity rivals, and in some cases surpasses our own. The Antikythera Mechanism's celestial precision, Damascus Steel's nanostructures, the Baghdad Battery's spark of electricity, these weren't accidents. They were the result of sharp observation, relentless experimentation, and a deep understanding of the natural world. Take Roman concrete, for example. While our modern bridges crumble after decades, their seawalls stand strong after 2,000 years. Or the Mayan astronomers tracking Venus's cycles with telescope-less accuracy. These weren't just lucky guesses, they were calculated, systematic breakthroughs. Even everyday conveniences like the thermopolia's heat-retaining pots or the Persian windcatchers cooling homes without electricity reveal a sophistication we're only now beginning to fully appreciate. What's equally fascinating is how many of these technologies were lost, sometimes for millennia. The recipe for Greek fire vanished with the Byzantine Empire, while the secret to forging Damascus steel disappeared into history. It makes you wonder how much knowledge has been erased by time, war, or simply lack of documentation. And more intriguingly, what forgotten innovations might we still uncover in crumbling manuscripts or buried ruins? This isn't just about marveling at the past, though. It's a challenge to our present. If ancient cultures could achieve so much without computers or precision tools, what does that say about human potential? Perhaps it's time we rethink the word primitive. After all, the Nimrod lens hints at optics advanced enough for telescopes centuries before Galileo, while Zhang Heng's seismoscope detected earthquakes with eerie accuracy. These weren't crude devices, they were solutions born from necessity and creativity, qualities we still value in today's engineers and inventors. So here's a thought to leave you with. The next big technological leap might not come from a Silicon Valley lab, but from a rediscovered parchment or an overlooked artifact. Imagine if we could revive the Antikythera Mechanism's gear calculations for space travel, or apply the Kanat system's water management to drought-stricken regions. The past isn't just a museum, it's a toolbox waiting to be reopened. Now, over to you. Which of these 50 ancient marvels left you the most awestruck? Was it the Viking Sunstone guiding ships through fog like an ancient GPS, or Heron's steam-powered inventions foreshadowing the Industrial Revolution? Drop your favorites in the comments. We love hearing your perspectives. And if this journey through history's hidden tech sparked your curiosity, don't forget to hit like, subscribe, and ring that notification bell. There are countless more mysteries waiting to be explored, and we're just getting started. Until next time, keep looking backward to dream forward. The ancients might have more to teach us than we ever imagined.